My name is Lindsay Verico. My teammates are Charlie Goodman, Thomas Thompson, and Vincent Novolino. Will be presenting about a design of an economical fast spectrum molten salt reactor. Our faculty advisor is Dr. Pomtag, and our industry partner is Dr. Balut with Idaho National Lab. Quick overview of our project. We're going to talk about why this project is important, some background research that we did, and then go into different aspects of the overall design that we settled on and some future work that will make this project actually feasible. So the image on the left is from the National Reactor Innovation Center. It's their vision for the future of nuclear reactors. Our project falls into the very end of this pipeline as a non-light water reactor demonstration reactor by the year 2030. That's coming up pretty fast. So our goal is to create a demonstration reactor to show the technology of a fast spectrum molten salt reactor. And to do this within the next decade, it must be quick to deploy. So our constraints are low cost, low power, and a modular design. That way, different elements can be built off-site and then come together on-site. Our design is also chloride salt-based. So the two major molten salt reactors that we researched that are in history were the aircraft reactor experiment. It was commissioned by the military to make long-range bombers. And in the 60s, Oak Ridge National Lab built the molten salt reactor experiment that we took a lot of inspiration from. Both of these systems are thermal, so they have a fluoride salt base. They have graphite moderators in the core, and their only comparison to our design is that they use a liquid fuel salt. Some advantages of molten salt reactors are the ability to remove fission gases while the reactor is operational, so you can remove large cross sections like xenon, which will affect the reactivity. There are also large temperature feedback coefficients, and salts have higher boiling points than water, therefore the system can operate at a much lower pressure, which makes it much safer. There's also some online chemistry control that you can do to maintain the enrichment throughout the fuel life. And the hallmark of Generation 4 reactors is their inherently safe design. So in particular for our reactor, we have a liquid fuel salt, so it removes any possibility of a fuel melt accident. Some disadvantages are the fact that we have a very corrosive salt environment, which will affect all of our other system components, and any in-core components experience a very high fluence. Particularly with fast and thermal molten salt reactors, some advantages of fast reactors in our case are the smaller size due to the fact that we don't have any in-core components. This also is better for materials. Some disadvantages though are the fact that we need a higher enrichment to start up and maintain criticality throughout life. This is expensive and could approach some legal limits. The design that we settled on is a cylinder with hemispherical end caps. It is 7 feet in diameter and is 14.28 feet tall. The vessel is made of HT9 steel to withstand the corrosive salt environment. And we've placed a stainless steel 304 reflector in 4 pieces on the outside of the core. That way it is not affected by the in-core fluence. This reflector will be lifted into place hydraulically and is used to achieve criticality.
To talk about the fuel salts in our reactor design, we use 19.3 weight percent enriched fuel, and that was chosen through a parametric study to optimize the fuel cost. In addition, we use 33% and 67% UCl3 NaCl fuel salt, which corresponds to the eutectic composition. So that eutectic composition is the composition that corresponds to the lowest melt temperature in the UCl3 NaCl system, and that has a melt temperature of 520 degrees centigrade. We chose NaCl because that's the hardest spectrum. What that means is that the neutron energy is the greatest, and that has greater breeding or transuranic burning potential compared to other fuel salts or carrier salts that we could have chosen. We enriched the chlorine in our design, so we removed the chlorine 35 from natural chlorine in order to increase the amount of chlorine 37. The reason is because chlorine 35 has a high absorption cross section, and so that removes neutrons from the core, decreasing the reactivity of our fuel salt. So what we performed was an enrichment study to search for two things: fuel salt enrichment and vessel diameter. So those are the two parameters we perturbed during the study. We used the UCl3 NaCl with the molar fraction identified before. We used Serpent-2 with an NF7 library that's provided with the code in order to model our reactor. Some of the assumptions that we made on our model, we assumed an average hot full power temperature for the entire fuel salt at 550 degrees C. We placed this SS304 at the most reactive position, so right at the core midplane. And we acknowledged that precursor drift would add about minus 250 PCM bias to our design. In addition, we included the total volume of the reactor plot would include the MSRE piping volume, because at the moment we do not have the total amount of primary piping in our system. So we assumed that in order to calculate the fuel cost. Since Serpent-2 is a Monte Carlo code, there's a standard deviation associated with the calculations we performed. For this particular set, we had a pretty high standard deviation. This was just because we're trying to map out the size of the core and not nail down the exact values. So I should present results from our enrichment study, which on the left gives the critical height as a function of vessel diameter and enrichment in atom percent, and the reflector worth. So the reflector worth, it decreases as a function of vessel diameter, and the reason is because the size of the reflector shrinks because we define the size of the reflector to be equal to the height of the cylindrical section. As we increase the vessel diameter, we decrease the amount of radial leakage out of the core, which also decreases the critical height of the core as well as the reflector worth. So we set a limit on our vessel diameter by limiting the decrease in the reflector worth, so that we would have adequate shutdown margin for our design. We also calculated the total fuel volume, including the MSRE piping volume, and the total cost of our fuel. And the total cost of our fuel determined the enrichment that we used. So we see that as we increased enrichment, we decreased the cost of the uranium needed for our reactor. However, there was a limit at 20% due to the legal definition of HALEU fuel, so high ASCII, low enriched uranium. And above 20%, we would enter into high enriched uranium for that definition, and that would add additional legal and regulatory hurdles we would have to go through. That would overall increase the cost of our design. So we chose 19.5 atom percent because it minimized that cost, and it gave us adequate margin to increase enrichment later on if need be for if any reasons our calculations were off. We conducted a reflector study, which made the same assumptions as our enrichment study, but we accounted for the 250 PCM bias for precursor drift in this calculation and decreased the standard deviation by running more particles and cycles. We started off with a large number of initial candidates and then started eliminating them based upon the performance relative to SS304. If it performed worse than SS304, we eliminated it. If the material was considered hazardous, so if it was a powder and be a lung irritant to the workers that would go in and repair the reactor, or if it contained a light nuclei, which would act as a moderator. We're a fast reactor, and so we would not want to moderate neutrons with our reflector. The final candidate was ultimately chosen to minimize the cost of the uranium and reflector, as well as balanced with the activation potential of the reflective material and the weight. So I give a summary of our results for our initial study. And we see that 3 of the candidates that are denoted with X next to it move on to the final, while the rest of them are eliminated based upon the reasons that I gave on the left. We see a couple, and again, we see quite a few different potential candidates, but because of the hazards associated with them or they moderate the spectrum, we eliminated them. So our final candidates, we see that we have SS304 winning out, and this is because though nickel and tungsten have lower overall cost, and nickel has a lower overall weight, SS304 does not activate nearly as much as nickel, and so we eliminated nickel because of the activation potential, which would complicate recycling or disposal of the reflector, and that would add to the overall cost for decommissioning. And we eliminated tungsten because the weight of it's almost double that of SS304, so that would complicate the hydraulics needed for our design. We also calculated temperature coefficients, so react temperature coefficient and Doppler coefficients for our reactor. We see that we have a pretty large temperature coefficient, minus 33 ppm per degree C, and this is due to the high expansivity of our fuel salts. We have a very low Doppler coefficient because of 2 reasons. There's less slowing down due to the higher average energy of neutrons in our reactor, and less uranium-238 targets because of the higher enrichment. And so these were ran to the the lowest standard deviation of all the studies, was these reactivity control and the shutdown margin calculations, which are ran to 15 ppm. We accounted for in the shutdown margin calculation a combined Doppler and density effect of reference from hot full power to hot zero power. We added in the assumption of precursor drift needed for our reactor control. We assumed one of the reflectors was stuck up, similar to a stuck rod criteria and LWR safety analyses, and a 10% uncertainty in the reflector worth, which is common for these shutdown margin calculations. The ultimate shutdown margin for our reactor is about 3% delta K.
So for the thermal hydroxide system, we have the primary, secondary, and tertiary loop. The primary and secondary loops have temperatures of 550 and 450 Celsius respectively, while the tertiary loop is set to the atmospheric temperature. The primary and secondary loops have nominal flow rates of 100 kilograms per second, while the secondary and tertiary loops have variable flow rates, so they change their flow rate to maintain the temperature of the prior loop. Coolant selection, we had to choose a secondary coolant salt to use. We had 2 main criteria. Firstly, we wanted the coolant salt to be chemically compatible with the fuel salt, for if there is a leak between the primary and secondary heat exchanger. While we also wanted the secondary salt to have a lower freeze point, so we can operate the secondary loop at a lower temperature than the primary and thus have a smaller heat exchanger. Lead to chloride, sodium chloride eutectic meets both of these desires. Next, we want to talk about pressure drop and pump sizing. The primary source of pressure drop in each loop is the heat exchangers, because it goes from a wide pipe of 5 inches to narrow channels in the heat exchanger. Some references have this. Scaling from references shows that the pressure loss in our system will be about 15 psi through each heat exchanger for both the primary and secondary loops. The flow rate difference is due to the difference in the densities of the 2 coolants. And using our equation for pump power, we can calculate that the pump power for both the primary and the secondary pump should be at least 10 kilowatts. The first of our auxiliary systems is our drain tank. This tank sits below the core so that in a loss of power situation, it is able to drain the fuel salt into a non-critical geometry. It is water-based cooling to prevent overheating of the fuel salt and it has an actively cooled freeze plug in the primary loop so that in a loss of power situation, the fuel salt will drain out and be walk-away safe that way. The next to our auxiliary systems is a fission gas removal system. This fission gas removal system has an interface between the fuel salt and helium gas. This allows the fission products that are formed to off-gas from the fuel salt, and a lot of these fission gases may have large cross-sections, so that's neutronically favorable. These radioactive gases are held in charcoal beds to give them time to decay enough before releasing them. Our next system is salt chemistry control. The salt chemistry control system actively works to maintain the salt chemistry over the life of the fuel salt. This includes removing hydrogen that builds up and solid particulates from the fuel salts.
As for the economic analysis for our molten salt reactor design, first understanding that a molten salt reactor is not, our molten salt reactor is not a power producing reactor, it is a primarily research reactor. Understanding such that you understand that overnight costs cannot be established for not producing power reactor system. So in order to produce our overnight cost for our molten salt reactor design, we must have comparisons of the small modular reactor economic analysis. So we use those percentages depicted above to establish our overnight cost for our molten salt reactor. Under the assumptions that a molten salt reactor can be analyzed at $5,945 per megawatt, and with our reactor system having a maximum operation power of 1,000 megawatts, we can establish a $5.9 million overnight cost. From this $5.9 million, that's when we implement those percentages. In the table to the right, depicted to the right, you'll see those cost analyzations calculated and the values are depicted. So for our system, we have about 29,000 kilograms of uranium at about $24 per kilogram, and that produces an overall amount of $77.9 million of uranium. For the production of our fuel salt uranium chloride, it requires about 15,000 kilograms of sodium chloride, which is also included into the total conversion cost of our uranium chloride or fuel salt. And that total conversion cost is about $27.1 million. Also, to operate our molten salt reactor designed properly, the fuel salt must be enriched to 19.3%. For doing this, you must include the SWU cost, and the SWU cost of our uranium was calculated as about $55.3 million. So that makes the fuel cost of our system the most large cost factor in our molten salt reactor design at about $172.1 million. We also included a 7% tax on the fuel product and the reflector as well. And most importantly, we included a conservative cost factor of 2 to in place a margin of error just in case of any assumptions or any mistakes were made in the economic cost evaluation. Also, our molten salt reactor design has a lifetime of 10 years under a 1% interest rate, and that makes the total cost, future value cost of our project, $405 million, which is about $38.7 million a year. Future work for our molten salt reactor design, we will need to validate our testing and our design with material testing, is coupled thermal hydraulics and neutronics modeling, depletion analysis, a design layout and construction, auxiliary system operations such as fuel salt chemistry testing, fission gas removal, accident analysis such as contingency plans just in case anything were to go wrong with our system, and the more thorough in-depth economic analysis without as much assumptions. These are the references we utilize to provide this molten salt reactor design. And now me and the group will entertain any questions or concerns, statements. Thank you.
All right, everything all right?
Yes.
Okay. One sec. We are the core optimization of a 2-year PWR fuel cycle using Formosa and Prism Group. We are Jonathan Crozier, Patrick Hartwell, Nick Meehan, Amelia Manhart. Our advisor on the faculty was Dr. Jason Howe, and our corporate sponsor was Framatome with Mr. Mike Savella. Ours is a multi-year project. We are in the second year. The overall goal for the project is to assess Formosa and see if it is an improvement over Prism's native solver. Once we've confirmed this, we plan to develop a coupling for using Prism with Formosa for loadout optimization. Previous progress from last year's group was setting up Prism on the NC State resources. They were able to get a near viable loading pattern using that. For this year's progress, the plan is to produce a 2-year optimized loading pattern that meets a set of constraints provided by Framatome, and to determine preliminary steps for integration of Formosa and Prism for generating test results. Starting from last year's endpoint, they provided this near viable loading pattern. It had a cycle length of 682 days, 4 days short of the target 686, but within the margin. It had 1,575 ppm of boron at the maximum point, and it had acceptable peaking factors as well. After we examined that, we wanted to check if it was possible to have a viable reactor with enough reactivity to make it through the full cycle length while also having the boron concentration within limits. We checked this by determining the minimum enrichment for a full core to have the desired cycle length. We created fuel assemblies with as little boron or gadolinium as possible, and then we increased it to the maximum amount to see if the initial reactivity could be brought within limits. Since it couldn't, we determined that we needed more burnable poisons in our assemblies. To make that possible, we requested the cross-sections from Framatome, and they provided them. After which, we were able to create this loading pattern, which satisfied all the requirements, but had room for improvement. After we had time to improve it, we moved to this one, which was a definite improvement, reducing the rod exposure so that we were within the limit, but not quite to the ideal, and having all other absolute limits matched, but not quite having as ideal. We were able to reduce the enrichment levels between the two cycles, after which we were given an additional constraint that there be only 2 different enrichments. This was the final loading pattern that we created. It satisfied all requirements and had only 6.2 and 5.95 as enrichments. And this is the one that we used for financial comparison against the previous group's loading pattern, for which I'll pass it off to Amelia.
So to complete the financial analysis, we made use of a code called Fuel RQ. It is a proprietary code of Framatome's, but we can still tell you a few things about it. It uses all of the same information as the inputs for Prism, such as the number of assemblies, the enrichment, the gadolinium content, that sort of stuff. And so you just basically take whatever you had to put together the input for Prism and rearrange it into the input for Fuel RQ, and then Fuel RQ tells you everything that you need to pull it off. It's a very versatile code. You can use it to calculate the uranium requirements for a single reload batch or up to 32 sub-batches. In our case, we had 7 sub-batches. Next slide, please. Okay, here we go. So the general method of how Fuel RQ would figure out everything that was needed for the total cost estimate, it would take into consideration the cost of the raw U3, then the cost to fabricate that U3O8 into fuel, and to store the fuel after it was fabricated. It would take into consideration the interest rates for the pre-reactor investments and use of the fuel in the reactor. And then it would take into consideration the conversion costs and the time for the enrichment, as well as any delays that may be occur during the fabrication, as well as the overall efficiency for the specific design and the number of assemblies in that particular design. And lastly, it will also take into consideration the total cycle energy and the cycle length in days, including any downtime in that cycle. What is important to note is that there is not any consideration for any profit that may be made by running the reactor. So if you are running this code for a power reactor rather than a research reactor, it will not take into consideration the money made back. Next slide, please. And so here we have a comparison of last year's design to this year's design. As you can see, our design uses a bit less raw uranium in the design, and so then therefore the fabrication costs are lower, the conversion costs are lower, and then the overall standardized work units are also less, because our overall average batch enrichment is less than it was for last year's design. So overall, we managed to trim down $5.22 million off of the design at the same time as making it a more feasible design. And so to talk more about the other side of our project, I will hand it over to John.
Okay, see, there we go. So to discuss the motivation for Formosa, the most relevant part of this, the goal of this project is to optimize a loading pattern as well as compare the optimization process from the manual optimization with a pre-existing Formosa algorithm with simulated annealing. So we have multiple design parameters that a core designer uses to evaluate a loading pattern, such as critical boron, core parameters, rod peaks, as well as where the fuel is going to go in the core. And all of these are factors that a core designer must take into account when designing a core. And Formosa uses a penalty function, metropolis criterion, LAM cooling schedule, a variable acceptance of the loading pattern, as well as parallel processing to truncate the optimization time needed to design a core on the fly that will meet a licensed reactor's parameters needed for economic feasibility. Patrick? Okay, so with regard to the simulated annealing algorithm, the basis of the algorithm is that there's going to be an objective function associated with the core parameters, and for each given core that's going to be modeled with a core simulator such as Prism or Simulate, the degree to which a core parameter fails to meet the designer's criteria will essentially increase an objective function, which pushes it farther away with a lower probability of being propagated to the next generation of solutions for loading pattern. Patrick? The LAM cooling schedule comes into play in that all of these loading patterns, once they're executed in parallel processing, are evaluated at each state point, which is one finite temperature essentially. And the temperature is kind of just a metaphor for the cooling and the convergence of the system as a whole. And the LAM cooling schedule is an algorithm within the Formosa simulated annealing algorithm, which simulates the cooling of a metal itself in a larger system of atoms as they cool to their equilibrium positions. And this is the same thing that happens with all the states as they're mixed. So all the states of the loading patterns as they're perturbed and the perturbations are sampled with all the parameters will end up converging to a state of equilibrium with each other that will result in a minimum, which will, at the output of Formosa, give you 5 loading patterns, which will essentially be what the designer can pick and then reevaluate for financial and economic feasibility. Thanks, Patrick. So the mixing of states is when there are perturbations at each parallel processing unit, and at each mixing state, there's going to be perturbations of such things as fresh fuel loading pattern, exposed loading pattern, shuffle pattern, fresh fuel enrichment, burnable poisons, and this is defined by the user within the bounds of the cross-section library given to it. And there's a certain amount of interpolation that can happen between cross-section libraries, which is also a user-defined function. So depending on the extent to which a designer wants to move within or outside a certain amount of enrichment or core locations, the mixing of the states can occur at a faster rate and also as a function of the standard deviation of all the pooled statistics from the different parallel processing units, which will end up resulting in an updated acceptance probability such that the higher quality solutions will be propagated much faster and the lower quality solutions are going to be eliminated over the course of the Formosa run. Next, Patrick. So the objective function calculation can be made with a variety of methods. One is the constraint annealing method, and the other is a static penalty method. And while there isn't a significant difference in the runtime of the code, both are implemented in the Formosa source code. And within the source code, there's different references, and you can pick one or the other. So there are multiple different methods of assigning a relative goodness to both the output, the core output parameters, which will be evaluated, which then gets translated into the code evaluating each loading pattern as a whole. Thanks, Patrick. So this is just a depiction of the way in which Formosa goes about spreading its parallel processing units. So it'll initialize a loading pattern, it'll establish a cooling step associated with that loading pattern, at which point it'll perturb that loading pattern into a variety and a large amount of potential solutions, which these NPI processing units will then evaluate continuously and then recollect themselves to pool their statistics and reanalyze a standard deviation and then define the extent to which they'll accept a certain number of solutions to be further perturbed in the next mixing of states in the next cooling steps. Once it's converged, you get your output solutions. Thanks, Patrick. Here are a few general trends from the data. You can see that the user has the option of varying batch enrichment, batch size, fresh fuel, the fresh loading pattern, exposed loading pattern, as well as the orientation map. And the number of solutions, so the acceptance ratio initially starts out on a very specific trend, branches out as the code runs, and the number of solutions increase in number, at which point the cumulative statistics grow to enough of a significant amount of size such that the code is able to then truncate at a much faster rate the number of things that'll be continuously reevaluating. Patrick. Here's some general statistics just for you to visualize the number of data points that are evaluated over the course of the Formosa run. And you'll notice that the convergence towards the very end of these graphs also corresponds with the updated exponential decay of some of the other convergence criteria of the previous slide. Thanks, Patrick. So this is where we're going to start to transition to the more fine-tuned details of the coupling. And Nick will be able to discuss a little bit about how we went about implementing changes in the source code with Formosa and where we made finer pointed details. And so you can see that we were looking into replacing the core simulator simulate with Casmo's cross-section library with Framatome's Prism, which is their version of a core simulator, as well as their cross-sectional library. And you'll notice that Fuel RQ is just towards the tail end of the optimization process, which is where we did our economic analysis. Thanks, Patrick. Oh, one back. And so here's where we start to edit the source code. And there's a few very specific functions that we made edits to and then recompiled. And take it away, Nick, with some of the other coupling stuff we did.
Thanks, John. So in terms of coupling the codes, we had two main approaches over the course of our project. We had one route, which was indirect coupling, which was the route that we chose first. And this would involve running the codes separately. So you would run Formosa's optimization process coupled with Simulate's core simulation ability. And that would develop your optimized loading pattern. And what we could do with that is we could transfer that into Prism by building an equivalent core and then run the case there, and hopefully it would be the same thing. However, we came up with a roadblock in that approach in the fact that the cross-section libraries between Prism and Simulate are different. So while Prism and Simulate are fundamentally the same in the fact that they are core simulators, the cross-section library generated by Casmo that feeds into Simulate is not the same as the proprietary version of Casmo, which generates the cross-section library for Prism. And this causes discrepancies between the two simulators in terms of the results they would get. So if you were to build an equivalent core in Prism, you would actually end up with different factors for, say, peaking or exposure, etc. So to circumvent this, we moved on to a direct coupling approach, and this would allow us to run just Formosa. And as John was saying before, you would do this by manually going into the Formosa source code, and anytime that it would call on the simulator to run a case, you would replace the call to Simulate with a call to Prism, and it would also take all the variables from the end of each of those simulator runs and feed them back in to build new inputs and run the optimization process yet again. Next slide, Patrick. So in order to do this, as I was saying, you have to edit a bunch of these subroutines that come in the Formosa source code, namely within the call simulate or build simulate input and the read simulate output. You would have to not only replace the call to the actual simulator itself, which we have already done, but you would also have to edit these subroutines within read simulate output that call on all the variables that are developed over the course of your run. And this includes the core maps, which includes the assemblies and their makeup, your isotopics, your exposure maps, your peaking maps, all of that for each depletion step, and that all feeds into the simulated annealing algorithm. Patrick, you want to go to the next slide? All right, so some of the future work that we're planning to do with next year's team is we're going to let them know to start with direct coupling rather than indirect coupling, and this will kind of just get them on the right path off the start in terms of coupling the codes together and making progress in that. We are also building tutorials to get Prism and Formosa running because we found that some of the main time-consuming steps in this process were just kind of getting the codes running, understanding what they do, and actually trying to see the little intricacies that go on between them and how to actually get them running together. And that's all. I'd like to open the floor for questions.
All good here.
Alrighty, I'm going to share my screen. All right, so ladies and gentlemen, you know me as Johnny. I'm presenting the work done by my group, Caitlin Blake and Dr. Wu, on the neutronics investigation on absorber materials for the high temperature gas reactor microreactor concept. Some backstory on this project. In 2017 alone, the US military emitted a whopping total of 560 metric tons of CO2 just in 2017 alone. To put this in perspective, that's more than what many industrialized countries will do in a year alone. Why so high? Well, we have a pretty vast military, and 40% of this on an annual basis is attributable to real estate commodities, such as heat, electricity, cooling. And my roommate is an ex-Marine. He can attest to the fact that we have people spread all over the world, but they are not living lavishly. They have very modest living conditions. But all the electricity demands are met by portable gas generators. Also, attacks on diesel transport vehicles account for about 50% of our wartime casualties. So to address this, the DoD would like to implement portable nuclear-powered generators. GE is a part of a team designing and building the high-temperature gas reactor capable of continuously producing a low megawatt thermal core output level, roughly 3 to 10 megawatts. And some basic requirements include a 3-year minimum lifetime, fitting into the 20-foot shipping container, weighing less than 40 tons, a quick startup time, and a quick, getting it shipped out of there, while also hoping to have semi-autonomous operation. So that kind of gives the gist of why this project has very important implications, and it is ready to make immediate contributions to significant problems that we are facing in our global economy. And this is how NC State was able to contribute. The image shown here is a radial 2D slice of the high temperature gas reactor system. In the blue, you see a helium coolant, the flow path through the core. The yellow is helium moderation, and there are 8 control drums surrounding the periphery. The green on the control drums marks where the neutron absorber materials are pasted. That's not the exact geometry, but the green is just there to give you reference for the time being. And the pink is where the triso-fuel spherical elements are implemented into hexagonal graphite blocks and placed inside of the helium coolant system. Actually, I'll go back to the initial slide. So here, just a quick naming convention. The system here has all 8 drums facing in. For the purposes of our examinations, all 8 drums exhibited similar characteristics, but ideally for operation, you're going to have 4 that are always facing out, so that way it can be used as a safety mechanism. But for our cases, all of them behave the exact same. We chose 6 initial materials based upon performance criteria and data gathered from different articles. And they are all subjected to the same MCMP environment, steady state BOC conditions, 1200 degrees K. And this is only for the case of a homogenized core, which you can see a depiction of in the bottom right corner, but just for the corner core. The way MCMP would track the criticality was by measuring birth, capture, and leakage of neutrons, and keeping measure of tallies throughout the mesh. And that is how the figure on the right was produced. This is the first slide for the results of our materials testing analysis. And it provides insight into how the different materials behave in comparison to each other in similar methods. So they all exhibit the same trend, really. There are slight variations when they are fully inserted, but for the most part, there is negligible difference between them. It begins facing in at the 0 degree angle insertion convention, and they are rotated counterclockwise until they are in the full out or completely facing away from the center of the core. As you can see, even with the 6 completely different materials, the net effect on neutron economy is similar, and they are all able to bring the system to critical. More results from our material testing analysis, which provides insight to the rate change of the K effective based on the rotation facing the core. This is a visual mainly for the differential K effective slope as the drum is rotated. Again, as with the case before, the materials exhibit a similar characteristic, but this has important implications for the semi-autonomous function of the microreactor system. A secondary goal for the control drum design is to have a linear K effective slope, so that way it makes insertion uniform. It would be much easier to control that way. But no matter what material you use, you see very similar characteristics here. So this was something that we aim to address moving forward. We address this by altering the geometry of the materials being applied. This will take the form of radius and arc length, where if you use the same amount of material to affect the radius as you do the arc length, having a greater surface area is more influential than having a larger thickness. So by using one material, for this we chose boron carbide, and making a variety of different geometric alterations to the control drums, you can see how it has a varying effect on the neutron economy, but all the changes are the same. It won't impact the slope of the characteristic line, but it will change the amplitude. And reproducing the differential plot, which for some reason isn't loading. Reproducing the differential plot, the objective here was to linearize this curve or to see if this is something that could be done by just simply changing geometries. That is not possible by having uniform changes. To do something like that, there would have to be more complex geometrical arrangements, such as changing the radius based off of the angle facing. So having a shorter radius at the 0 degree position, but having more thickness towards the periphery. So that way you can try to balance out and make the large portion of the curve more linear and the bottom portion more effective. I'm sorry, my screen just halted for a second. We used the equivalent uniform annual worth as the method for a simple and standardized analysis of all 6 materials on a similar platform. For this comparative evaluation, the absorber materials are considered as depreciating capital investments, and the rate of depreciation is determined by each material's lifetime, which we go into more details on the next slide. The depreciation charge was determined from the sinking fund method, and the overall yearly charge rate was based off of the influence of investment return, taxes, and insurance, and was kept standard for all of the materials. So that way we are evaluating the initial cost, the interest, and essentially the lifetime to give more insight to depreciation over time and how much a material is worth annually. And this is a figure that shows the lifetime, but also compares the lifetime with the price associated with 1 kilogram of that material. The materials with the longest lifetime are boron dysborium titanate, hafnium, and hafnium diboride. But as you can see, the 2 least cost associated materials are boron and dysprosium titanate. And that is the most impacting factor in the final value for the equivalent uniform annual worth. So given the available options and similar performance aspects of all the materials, cost considerations are really the primary influencing factor in selecting a material. And as you can see, we have 2 very competitive options with boron carbide and dysprosium titanate, and everything else is a non-factor at this point. So as I said, boron carbide, dysprosium titanate, most optimal candidates. However, considerations of factors beyond the scope of our project should also be considered before making a final economic decision. System fit, for example, is the thermal conductivity of the element sufficient to survive in this system without cracking? From what our research said, yes. But all we really had was information from different scholarly articles written in the 80s or maybe the 90s. I would have a hard time putting my faith in that alone. So it's easier to get information if you can pay for it. System response, I can give more information on this in the Q&A section if anyone is curious, but essentially how the system would respond to the presence of boron versus the presence of titanium. And then material lifetime. In our analysis, we examine the control mechanism and its effectiveness over time. We did not investigate material integrity over time. So that is something that will be considered or should be considered. And as I mentioned, the introduction of more complex geometries. The plot on the right shows the physical efficiency of a material, which is explained best through the physical phenomena of over several neutron interactions, the thermal cross-section of a material is going to depreciate over time. This is going to have an accumulated effect when elements are in a constant exposure environment. This plot is over 4.5 years, so it gives a pretty good insight as to how boron carbide, which is the material labeled on number 1, compares to dysprosium titanate. They'll both have the same type of efficiency at the end of the 3-year period, but that's when the boron carbide drops off to about 50% of its initial efficiency. So the exact nature of material integrity over time was outside the scope of this project, and collecting the exact information on this topic does not come free. Given the limited resources, it's tough to discern what margin of efficiency at the end of the material's lifetime is sufficient to justify reuse. Because remember, the lifetime of these microreactors are only set to about 3 years, and materials can outlive that. So at what point can you justify reusing a material over time? That's something that we cannot determine, but it can be considered in one of two ways, paying to find more information or determining that information on your own. So the first time you send out these reactors, do you include different materials for absorption, recall them in at all the 3 years, and then send them to a lab to be examined? That's one possible outcome, but while this thought of recycling should be entertained, you should also keep in mind that it might not always be more economically attractive to reuse the rods if it comes at, limiting other aspects of power operations. So say if recycling the control drums means you have to operate at a lower initial power level, that will come at some cost. When you're producing power to the grid at from a large power plant, reducing your power output is a big hit economically. But when you're just supplying some basic electricity to the Marines out in the Middle East, they can go with a few power outages, or it's not that big of a deal. So you just have to keep in mind the different type of environment that this is going to, as opposed to what we usually deal with in the big light water reactor setting. So as I've showed you, I'm going to wrap it up, but there's really a lot to consider that will influence what absorber is the best material to choose, especially given the unique circumstances, the environment of the HTGR reactor, the scale and the use. And while we didn't have all the resources necessary to give a definitive answer about what is the best, we can say these are the two materials that should be considered as the solutions for the problem. And at that point, I'd like to open the floor to any questions from the audience.
Well, thank you. I think that, this was, an interesting project as per so many discussions that I had with you. Of course, as I see the comparison between boron carbide and dysprosium titanate, you can say that I have a better cross-section, with the dysprosium, but it's a very poor thermal conductivity and even much lower melting temperature. So finally, I think that your choice for boron carbide is the best choice. I think we discussed this previously, right?
If I had to give one answer, I would say boron carbide. Yes.
Yeah.
Y'all are in agreement that boron carbide, especially with General Electric, already being familiar with the compound, I think we all agree that boron carbide was the best material.
Well,
given the life of this project, there will be a couple of years to continue evaluation, and in that time, I think it would be a good idea to gather, more information on dysprosium titanate, so that way you can make the best decision. Because, it'd be helpful to consider all options and make the best choice possible.
Yeah, and then moreover to the economic analysis, a lot of the materials like europium oxide and boride actually are getting cheaper every year. So again, like in a few years, it might be beneficial to reanalyze dysprosium titanate and maybe hafnium diboride again. But overall, yeah, boron carbide was definitely our number one.
Yeah, you mentioned hafnium, Caitlin, and I think that hafnium will remain expensive even over the coming years. Yeah. Well, thank you.
Thank you.
So,
hi, good job, the team. It seems like you had a lot of constraints to work with, so that's good to hear. This is the first presentation where we only have one person speaking. Can you kind of walk through what the team looked like, who did what? and how that teamwork worked?
Yes, I can answer that question. So in short, we split it up into a couple different regions. In terms for what I did, I ran the MCNP code for the control drum alterations with the absorber and wrote the code to, or altered the input file given to us by GE to make those changes to the absorbers. Caitlin's job, she performed the economic analysis, and on top of that, she also helped run some cases for the different materials before the geometric alterations. And for Johnny, along with us, we all did individual research on different materials to test in MCNP, and he also looked into the MCNP code to create the neutron flux mapping to see about any peaking factors around the absorbers.
I have a question for you.
Sure.
This is George Lipscomb. You had shown in your comparison the materials that it looked to me like it was on a per kilogram basis that you did the comparison. And I was just wondering if that was true in your comparison, is the amount of material that's required for each application the same based on that to negate any differences, or whether you considered that as part of it? And maybe I missed it.
So in terms of, we thought it would just be best to analyze the material per kilogram for two main reasons. One, we were not given the exact dimensions of the reactor. We were not able to have that information. So we didn't have specific volumes and masses to evaluate off of. And because each material performed very similar in the MCNP testing, we thought that it would be also a comparable amount of material.
And given the results from the K-effective analysis, all materials had roughly similar influences on the neutron economy. So even though we don't know the amount of absorber that is specific to the environment, we can say it would be roughly the same amount that is required. So regardless of the case, we felt pretty safe doing the economic analysis on a standard unit of measurement.
So you're saying that the densities of the material is similar between them? Is that what you're saying?
The densities would change, but the impact of a standard amount would be the same. So when we ran the initial cases, we would have the same volume taken up. The densities would change, but not to a large degree.
Okay, thank you.
Yeah, I have a question for Johnny.
All right.
Johnny, could you go back to the cross-section of the microreactor core?
Yeah.
Okay, you mentioned that I can't remember if you had mentioned this or not, but you mentioned it uses a triso fuel, is that correct?
Yes.
You talk about how the triso fuel is loaded and arranged in the core. Is that information you guys were given?
Yeah, I could talk about that.
Okay.
So this is what I know about triso fuel. It's spherical and it has different coating layers on top of it. And these spheres are loaded into cylindrical arrangements, which we could best compare to fuel pellets. And the gaps are filled with either a liquid matrix or a dry graphite powder, which is what keeps them in place. And the pellet is then compacted and heated to solidify it. And multiple pellets are stacked up on top of each other and loaded into this hexagonal grid of graphite block. And that's used to create the fuel compact, which is most easily relatable to what we call like fuel assemblies. And then the yellow sections in between are the helium flow paths.
You're saying that the helium flows anywhere that's yellow is essentially like a helium duct, is that right? For the coolant?
The yellow regions of the HTGR system are the reflector. That was a misprint on the slide. The helium is the yellow regions are the reflector.
Okay. Oh, it says blue. Blue is flow path for helium. Okay. Never mind.
Yes, yes, that's correct. Blue is the flow paths for helium, and the yellow regions are the reflector.
Okay. Thank you.
Yeah.
Does that answer the question about the TRISO fuel though? Because it's arranged, compacted, and then embedded in the graphite blocks, which are placed in certain arrangements.
That effectively covered it. Yeah.
Okay, cool. Hey, Dr. Zeno, is your mic turned on? I think I saw you talking, but I think I saw you moving your lips, but I couldn't hear anything you were saying.
Can you hear me now?
I can hear you now.
Yes.
Okay. Yeah, I had the mute on. Sorry. Yeah, no, I was going to comment that, yeah, the yellow is the moderator, the graphite moderator region.
Got you. Yeah, misprint.
Yep.
Thank you.
Hey, this is Scott Bowman. So you looked at thicknesses of the absorbent material as well?
Yeah.
Yes.
And you found that the thickness didn't matter so much?
Not as much as varying the arc length, but thickness did make an impact.
Okay. And the physics as to why that's so?
More impact, more absorption. And if there's more being exposed to the face of the core, that's going to be manifested by the arc length because there's just more exposure to the environment. But if you're layering it, it's going to be less available.
Good answer.
Thank you. And if that's it, I would like to take a moment to thank Dr. John Zeno and Jenny from GE for a fantastic year. We had a great time with this project, and we learned a lot even beyond the scope of what we presented. So thank you very much, guys.
And our faculty advisor.
And Dr. Wu, yes.
Thank you.
Wonderful. Thank you, team. Can we have team number 4 come up, please?
Hi, everybody.
Hello.
Hello, hello. All right.
Oh, I was muted. Is everyone ready?
We are ready.
Awesome, awesome. So good afternoon, everybody. My name is Mohsen Zakayeb, and along with Justin Cohen and James Harglerode, we are the high enrichment, high burn-up loading pattern optimization for a 3-loop Westinghouse pressurized water reactor. Not to be confused with the 2-loop Westinghouse pressurized water reactor, which will be the next group. We're just slightly more awesome. Our NCSU advisors are Drs. Avramova and Ivanov, and we'd like to thank them for everything they did for us this semester and helping us out and keeping up with our questions and just constant nagging, as well as our Westinghouse advisors, Mr. Durham and Mr. Tyler. Thank you very much. And as you can see my background, since we were doing this meeting on Zoom, we thought we'd take some creative liberty. And so the background picture you see, which will be explained during this presentation, is the loading pattern that we designed for this 3-loop Westinghouse PWR. Next slide. So our presentation outline for today will be as follows. We will begin by talking about the rolling planes design constraints. Rolling planes is the pseudonym given to the reactor. And can you go back just one slide, please? Thank you. And we will follow that up with the core design process that we took, and then we will share some of our results comparing our preliminary work with ANC and how the process we took developing this loading pattern and where we ended up towards the end. And we will end off with some safety analysis and checks.
Okay, so this is the introduction to the reactor that we were dealing with. This is Rolling Planes Unit 1. Or RP, it's more or less a code name for the actual reactor. So this is a real Westinghouse pressurized water reactor, 3-loop core, 2,775 megawatts thermal with a hot full power core limit temperature of 537.5 degrees Fahrenheit. So what our overall goal was for this project is we were tasked with developing a loading pattern for cycle 30 with a target cycle length of 690 equivalent full power days, which is around 22.7 months, and a target end-of-life boron concentration of 10 ppm. So there was an additional cycle 29, which we were handed off, and our task was to develop the next cycle to achieve this extended cycle length. And historically, Rolling Plains has been fueled with 4.2 and 4.5 enrichment. However, to meet this extended cycle length, we had to test with assemblies up to 7% enrichment to meet that cycle length. And so this is what we were handed off with. This is cycle 29, the previous cycle with the 4.8, 4.4, and 4.2% enriched. So you can see that with this lower enrichment setting, it's more like the core interior is more of a checkerboard, and there's kind of this ring of once burned fuel and like a thinner out, like a more thin ring towards the periphery of the higher enrichment. And so getting this layout of the previous loading pattern was really helpful to taking this a step further in designing cycle 30. There's a lot of differences between how you go about designing this 29 versus 30, because 29 is low enrichment. So this was a good starting off point, but a lot of the strategy that goes into designing this LP wasn't necessarily applicable. So these are the governing design constraints that we use to test each LP and determine whether or not it was viable. The number one is energy, the 10 ppm at 690 equivalent full power days. So that's like the overall, it has to meet the cycle length. And then number two was our all rods out peaking factor, our FDH, has to be less than or equal to 1.55. And this constraint was really the one that we shuffled the core around the most and like did the most assembly movements to get under that 1.55. It's easy to meet your energy constraint if you just load in a bunch of high enriched fuel, but to meet the peaking constraint was definitely the hardest one. We also had to have a hot zero power, MTC at all powers had to be negative, and our fuel inventory. So we were tasked with using less than half feed assemblies of like the core. So we can use half fresh assemblies and half previous burned assemblies. This is a challenge when going to extended cycle lengths because you really want as much fuel enrichment loaded into the core as you can to meet that cycle requirement. And so that was our limit, was less than half. Then we have our rotted peaking factor, FDH, is less than or equal to 1.606. So that's with the control rods inserted to their rod insertion limits. And we also had shutdown margin greater than 1700 PCM. Our peak pin burnup is less than 70,000 megawatt days per MTU. So that's above like a standard burnup that you would typically allow for. So what we did for this project is, because it's high enrichment and high burned up, we pretty much pretended that the NRC would allow for a little bit higher burnup, like as that's kind of like where the industry is pretty much going. And so additional note was all the feed assemblies that we would put into the core had to be greater than or equal to 5% enriched. And that just also helped us to get by with the energy requirement. And then finally, we had the rod ejection limits. We'll talk about this a little bit more later, which is really important for the safety checks. So to talk a little bit about our core design process. So when utilizing design requirements for cycle length, the first thing you have to do is figure out from the previous assembly which of those now burned fuels like assemblies are viable and can have enough reactivity and high enough K infinity to be used in this next cycle. And then once you get an idea of how much reactivity you're pretty much getting from the last LP, you can then get an idea of how much new assemblies and how much enrichment you're going to have to add to get to that cycle length. And then we also have to consider proper fuel placement. Once you've done that, the goal with the fuel placement is lowering neutron leakage, a smooth power distribution, and the control rod insertion effects. So another way you can get by with meeting the cycle length, besides just adding a bunch of enrichment and fresh fuel, is to be strategic in your neutron economy. you put fresh fuel on the periphery or a bunch, that's not good for your. You have a poor neutron economy and you can't meet your cycle length. And then additional fuel assembly placement criteria that we used, which was really important, was to limit the total fluence to the baffle of the reactor, because we didn't want to be bombarding this already fairly aged reactor structure with neutrons. So that was also definitely a big factor in designing our LP. And then after we do that, we implemented burnable absorber. And for this LP to work with the relatively high enrichment and high burnup, we used IFBA, which is Westinghouse integrated fuel burnable absorber, and gadolinium. So we were able to use both around the core where we needed to limit the peaking. So the GAD was more so used less sparingly throughout the whole core to reduce the overall peaking throughout. And then the IFBA was kind of where we attacked the assemblies that had peaking issues. And then those also help to reduce the maximum boron concentration and and then those are also of concern for your MTC and ITC limits. And so to do this, we used Westinghouse Advanced Nodal Core Code ANC. So the code was running, and it's a really robust code, but to get it to really smooth runs for our purpose, the things that we had to do before we started running were, like I said earlier, organize the existing burn fuel by reactivity, the K infinity, and the burn up to get an idea of what fuel assemblies from the previous cycle we're going to be using. And then we also had to create and implement the fuel compositions. So because of these high enrichments with the varying burnable absorbers, not all these fuel compositions were created when we were given the code. So a lot of them we had to construct, particularly for like 6% and 7% enrichments. We had to sort of more or less customize our fuel compositions. And then we also changed the depletion to time steps to get a better visualization of when we hit that 690 days. And then we also searched through useful edits. That's just more of a comment for like how we sorted through our ANC results. And we also had to edit the ANC to output the information that we needed for the safety calculations. But one of the more important things that we developed through this core design process was this idea of test programs versus full runs. So what we would do is, because we kind of started off with a fresh slate and we weren't really sure what was going to work, we would have these test programs where we wouldn't run the full depletion to 690 days. We might just run for a couple of days just to get an idea of what that beginning of core peaking is like. Because if it's super high right at the beginning and we know it's not going to be a viable approach, we don't have to run the full duration to see that, just to see that it won't work. And the reason why we needed to do that was because the code does take some time to run. Like a full run could take around 40 minutes, but with our test programs, we can just see within a couple of minutes whether or not we're starting off good or bad. And that really helped us iterate on our design quickly. And with that, I'll hand it off to James.
All right, so using those test programs, we were able to go through several hundred LP designs in a effort to develop the one suitable LP that we ended up using to meet all of our constraints. And initial design approach was low leakage approach. You achieve the longer life cycle of the core. Place the burn fuel on the periphery of the reactor core to improve the neutron economy and to lower the leakage onto the reactor vessel. We placed feed fuel into a ring of fire within the core interior to improve the neutron economy. And we developed an 8th core symmetry despite being given a 4th core symmetry of paired burn fuel assemblies. We basically just mirrored the fuel assemblies on each 8th to make it easier to reorganize the reactor core between LP designs. That way it would save a lot of time and effort. We use GAD to promote an even burn throughout the core life cycle. So we basically just push down the FDH spikes throughout the life cycle so that you're not having peaks at one particular time. And then we use IFBA to reduce the beginning of life cycle FDH. It was definitely like a balancing act. You had to consider the effects of every single thing you did whenever you were working with it. Next slide, please. This is one of our initial attempts And as you can see in the boron section, at the end of it, you had a 331, which is definitely not any kind of cycle length requirements that we had. And then if you look in the FDH section, you see the first case had a 1.9 FDH, which is way above our our constraints of 1.55. And so in order to work on this, we had to increase our enrichment. We had to add more burnable absorbers, and we had to have like a better placement of our feed fuel assemblies in the reactor core. Next slide. So this is one of our this is LP 694. It's one of our last runs that we did, and we managed to achieve getting the core energy to above 10 ppm at the end of the life cycle, and our FDHs all go below 1.55. So we managed to meet both those accomplishments. Our beginning of the life cycle boron concentration was a little high, but with the fuel assemblies we had in there, it was a reasonable approach, and we did still meet all of our other safety checks and requirements.
Okay, so this is what that LP looked like in the end. You can see the red is 6% enriched, the yellow is 5%, the light blue is once burned, and then the dark blue is the twice burned. And it kind of has elements of like the ring of fire approach, but it's more aligned with what's called a bullseye. You can see like there's a more stricter box of high enriched fuel surrounded by with the interiors once burned, and then you have a fresh 5% right in the middle. So this was really one of the best ways that we could manage our fresh fuels and still meet peaking. And you also know that to increase our neutron economy, we had barely any fresh fuel in the periphery, where only one side of the four sides of the fuel assembly in each quadrant was exposed directly to the core periphery. So that very much went a long way in limiting our neutron leakage. And also we were able to get by with only using two types of feed enrichments, 6% and 5%. And that was one of like a secondary goal kind of to help with the manufacturability, so the manufacturers can focus on just producing these two enrichments instead of more than two. And then here's a comparison of cycle 29, cycle 30. So you can see on the left, it's kind of the evolution from the low enriched to the right is the high enriched. There's some interesting similarities and differences between how these cores turned out. You can see we definitely got some good ideas on where to put, especially our twice burned fuel. Definitely was only really viable on the core periphery, like on the most out core possible. And then there's also similarities where we have this red, which is our 6% ring, is kind of where the cycle 29 had their 4.8 and 4.4 enriched. But then where it differs the most is the most core interior, where this takes on more of a checkerboard approach with fresh fuel and burn fuel, and we have again this bullseye effect. So yeah, this is kind of speaking of the differences between the design approach that you would take when doing a low enriched versus high enriched. There's certainly other ways to load in fresh fuel in cycle 30 to meet the cycle requirements, and this is just one of the ways that we found works the best and meets all the requirements.
Yes, so these are our results for both our limit as well as our safety analysis limits as well. As shown earlier, our energy requirement was met at 13.9 ppm concentration for boron at 690 effective full power days. Our ARODS, our ARO F delta H was also met. One thing about the bullseye pattern is that something that is good about the bullseye pattern type of core is that it is easier to get longer cycles out of that core. However, it is harder to meet peaking limits. So it was very good that we actually met these peaking limits with a good amount of margin as well. For our safety checks, the first one we did was the moderator temperature coefficient. So we want our moderator temperature coefficient to be negative to avoid any positive feedback loop in case of a positive reactivity accident. And our most limiting case for MTC was the hot zero power case at the beginning of cycle. And and we actually got our MTC to be negative at negative 2.06 ppm per degree Fahrenheit. As for our fuel inventory, we needed our assemblies to be at least 49 to 50% of our assemblies to be feed assemblies, and we actually met this goal with 49% of our assemblies being feed assemblies. For a rotted peaking factor, this is when the control rods are at a real position or rod insertion limits. We also met our F delta H or peaking factor limit at 1.598. For our shutdown margin, which is basically we want to make sure that throughout the entire cycle that the core is running, that we can shut down at any point, and the most limiting scenario for this is at the end of cycle due to the boron depletion at the end of cycle. And we actually passed this limit as well with 3,894.755 PCM. For a peak burnup limit, we easily passed this limit, and actually even though our peak burnup limit was increased to 70,000 megawatt days per mega thermal units to allow for the highly enriched core, or to accommodate the highly enriched core, we actually can meet the peak pin burnup even with current industry standards at about 60,000 megawatt days per megawatt thermal. So this was a very good outcome for our core that we designed. Next slide, please. And these are just some graphs to show a physical representation of what we discussed in the last slide. On the left, you can see the boron letdown curve. As the burnup increases, we see the boron concentration decreasing. On the right hand side, you can see the F delta H versus burnup graph. We graphed both the all rods out scenario and the rotted or real rod insertion limit F delta H scenarios, and you can see that we meet both of those limits for both the all rods out and the rod insertion limits. Next slide, please. Thank you. The rod ejection limits. This is a safety analysis that we ran, and for conservative measures, we actually assumed that the highest worth or the highest rod worth would be the rod that would be ejected from the core. And so, as you can see, that we ran the rod ejection limits or the rod ejection safety test at both the beginning of cycle and end of cycle, and in both the hot zero power and hot full power scenarios. We successfully met the maximum ejected rod worth and the maximum FQ for all these scenarios. However, we exceeded the maximum burnup at the hotspot for some of these scenarios, and the reason for that is because we have a highly enriched core. And if we were allowed to increase some of those targets, like we did with the nominal maximum burnup, if we were allowed to increase some of the target limits for the rod ejection limits as well, we could also easily meet the maximum burnup at a hotspot with this core. Next slide, please. And now talking about the economics, you can have a great core, but if it's not economically viable, it's not a physical core that we can put into a reactor. And so there's a lot of numbers on this spreadsheet, but I'm going to just touch on a few important numbers. The economic analysis was done thanks to a spreadsheet provided by Westinghouse that they use for their that they use in the industry for their cores to see if they're economically viable. As you can see here, that the yellow cake requirement, which is the actual ore, was about $649,253. The important number here is the separative work, which is the work required for enrichment. And obviously our work requirement for work required for enrichment would be slightly higher than the standard enrichment core because we're using higher enrichments. And so this was slightly more expensive, but the really big number at the end of the day is the number you can see at the bottom right corner of the spreadsheet, which is the price per megawatt hour. And we actually achieved $4.637 per megawatt hour. When we consulted our Westinghouse advisors, they told us that this was actually within the viable range for an economic analysis done on a core. However, it was on the higher end of that range. And the reason for that, it makes sense it would be on the higher end because this is a high initial fuel cost. This is a first time this type of core would be designed, and so it would have a high initial fuel cost. However, when we switch to transition cycles, we will have more valuable burn more valuable burn fuel for our next cycles, and thus we will require less feeds in the future. Right now, we're using about 77 feeds in feed assemblies, which is about 49% of the core. But in the future, we would require less feed assemblies, and that would dramatically lower the cost, especially the SWU costs or the separative work costs. Next slide, please.
I think that's it. One thing to add about the economics with the high enriched mentality is it is like you do have like the high initial fuel costs, but the idea behind it is you pay more up front, and then over time with these, as Moses said, the more valuable high reactive burn fuels allow you to load in less feed fuels for the remaining cycles after that, and then you start to see more economic gains as through the next cycles. So that's really it. And yeah, questions.
Thank you. And we yield our time to any questions.
Good.
Hi, I have a question. Can you hear me?
Yes.
Okay. I don't remember the slide number. I don't think I saw slide numbers, but it was the slide with the limits imposed by Westinghouse for your research.
Yeah.
I think it's the third slide.
Okay. So were you provided any kind of information on how these limits were set, or did you do any kind of research on how Westinghouse goes about setting these limits? And the follow-up on that is, I think it was Justin that mentioned you aim for the MTC to be negative. Why is that?
Okay, yeah, certainly. So to address the first idea of like how Westinghouse comes up with these numbers is particularly for the FDH, that has built in 8% uncertainty into it. Part of that is computational. Part of that is unknowingness in the manufacturability of how precise the fuel assemblies are in the enrichment. So that's kind of how they arrive at the FDH. Like overall, the FDH of how they limit the peaking factor, that's really set by how like thermohydraulically how energy dense can you have one particular assembly, and how effective can you be at removing the heat from the hot assembly. And then for the second part, the MTC really should be negative, because if it's positive and your moderator temperature goes up, and the temperature goes up, you would have a positive feedback, and then that's a continuous positive feedback cycle, which is dangerous. And so it's a safety consideration, so that when your moderator temperature goes up, it inserts negative reactivity into the core to bring it down safely. I think that got it.
Yeah, thank you.
Thanks.
Okay, there's a question in the chat. Did you consider using enrichment greater than 6% weight?
Yes, so we did test with up to 7%. The issues you get with the peaking are kind of, at least with our ability, are out of our ability to really limit with the burnable absorber. So so the FDH really limited us going above 6%. It definitely is possible that we can use less feeds if, per se, we use maybe 6.2 instead of 6% enrichment, and then maybe we can use more burn fuel. That's something, like, there's definitely a little bit more room to optimize in terms of that element of increasing the enrichment a little bit more. Yeah.
And especially since our core design, which was a bullseye pattern, one of the biggest challenges with that type of design is the peaking factors. And using 7%, we saw that it was really difficult to meet those requirements. But as Justin said, if we tweak some things, including the number of feed assemblies we're putting into the new core, we could perhaps meet those requirements, especially if we go somewhere between like 6.2% instead of 6, as Justin said, or even 6.5%.
So another question: when considering your overall designs, did your team consider general design criteria?
Is that so? By general design criteria, do you mean like the material constraints, perhaps, or and is that what's meant by general design criteria? Like so our criteria for this project was specifically to meet these design constraints. I don't think we considered any material constraints, if that's the question.
Okay.
And that's because it's outside
Like,
of our project, and that's a whole project by itself.
Yeah, the material constraints really comes from the peak burn up and the pins allowed. Yeah, does that get it?
You kind of answered the question, but not really. But thank you. The general design criteria is just a regulatory criteria recommended by the NRC.
Okay, yeah.
Oh, okay.
Yeah, we really.
I'll answer that. Those design limits. So the NRC gives those design limits to Westinghouse, and Westinghouse creates their own design limits in a more confined section to kind of easily make sure that their all their field assembly, designs are more than acceptable to the NRC, which allows them to get their their designs implemented faster and accepted faster.
Yeah, exactly. Like I think it is that we worked like within the envelope of the general design criteria. Like the design constraints we were given were already like reduced to what they're allowed to do.
Yeah.
And I think I can see the chat. So there's did you work to confirm the Westinghouse economic assumptions? That part we didn't spend as much time doing that. We took or actually I think Molten did. Yeah, you got that.
Yeah, so if you can just scroll down to the economic slide. So yeah, we didn't do a very in-depth analysis of the of how Westinghouse does some of those calculations, especially for like pre-operation carrying charges, operating carrying charges, and spent fuel disposal. But for Yellow Creek requirements, we did cross-reference that with current prices in the market, as well as current industry standards. Same with the separative work and the conversion requirements, and they were pretty much similar. There are small differences, but that's expected. But as for the operation carrying charges, which wasn't extremely relevant to the calculation that would change our project versus a standard core project. So we didn't go much into those prices, but for the Yellow Cake requirement, conversion requirements, separative work, we did cross-reference that with some industry standards. Yes.
Okay. And then also I see, is there a regulatory licensing limit on the max enrichment? Presently, yeah, it's at 5%. So, but the way we kind of see not me, but like the way the industry seems to be moving into these higher enrichments, like the way we move forward was more or less pretending the NRC allows higher enrichments. Presently, it's about 5%. Yeah, and then recognizing the time value of money, which loading pattern is ultimately the cheapest in the long run. It is our research that thus far showed in the long run, it probably is better to go to high enrichment, high burnup and do the longer cycles. Like how we kind of talked about, you face this scarier upfront charge with high initial fuel costs to get to that cycle length, because you're dealing with fairly low reactive burned assemblies. But over time, through various cycles, those burned assemblies from the high enriched cycles are valuable to the point where in the next cycles you don't need as many feeds. And that's like that's part of the economic strategy behind why it's favorable to do that. But then you're also getting at lower outages. So if you look at like a 24-month cycle versus an 18-month cycle, I think you just like over like a common denominator, which I guess would be 40, or like you end up having less outages over time if you increase your cycle length for a given discrete period of time, and that's just more time putting megawatts out, and you increase your revenue that way as well. So overall, I would say yes, it is favorable to go to high enrichment over the long run.
Okay, thank you, team.
Thank you.
Appreciate it.
Let's have the next team, team 5.
Hello.
Hello.
Hey. All right. My name is Spencer McDowell. I'm joined today with
Amadou Tronca and Chris Gozum, in association with our faculty advisors, Dr. Maria Abramova and Dr. Kostin Ivanov, and our industrial advisors, Mr. Baxter Durham and Mr. Blaine Taylor. We are going to present today the high enrichment, high burnup loading pattern optimization for a 2-loop Westinghouse pressurized water reactor. We'll begin with a brief project overview. So we are designing and optimizing a high enrichment, high burnup loading pattern for a 1677 megawatt thermal 2-loop Westinghouse pressurized water reactor that will be using a specified fresh fuel inventory that will meet the safety constraints such as F delta H, moderator temperature coefficient, and so on, and also its economic requirements such as the cycle energy and the fresh feed assemblies. So if we look at the repository of fresh fuel enrichments available to us, we're using high enriched fuel, which is above 5%, which is the industry standard. So 5%, 6%, and 7% were available for us to use. These also use IFBA, which is integral fuel burnable absorber, and gadolinium, denoted as GAD. So if we look at the economic requirements, we see that the fresh assemblies must be less than 60. The core has 121 assemblies in it, so less than 60 is approximately half of the core as fresh feeds. And the effective full power days must be greater than 690. This is a 24-month cycle. 690 days is approximately 24 months. Looking at the safety constraints, our F delta H again must be less than 1.55. This is the most difficult constraint to meet and will be explained later on. The rotted F delta H must be less than 1.66. Hot zero power MTC must be less than 0. Our energy at the end of our cycle must be greater than 10 ppm. The peak pin burnup is set to 70,000 megawatt days per metric ton of uranium. This is higher than the industry standard currently, but with more accident tolerant fuel claddings, this is expected to be something that can be used. And finally, the shutdown margin is set to be greater than 1700 PCM. So if we take a brief look at the codes used, first we used ANC9, which is Westinghouse's proprietary nodal code. And what that does is first creates a cross sections for us to generate. This was done for us by Westinghouse due to the extensiveness of creating the cross sections. So using those cross sections, you then develop a loading pattern, which is to be loaded into ANC, which then gives you certain margins such as your safety calculations, your operational calculations, and your safety thermal, which can be loaded in a Viper but was beyond the scope of this project. And doing all that, you can then report your design. We also developed a multi-pattern loading tool, which was developed in C, which Amadou will explain to us more.
So yeah, as you guys heard before from the 3-loop team, they did the multiple runs to get like a variable pattern. So for our team, we decided, yeah, we're gonna need like a bunch of runs to at least get a variable pattern. So to do this, we just basically develop a multi-processor C program. So this multi-processor C program basically runs 20 loading patterns all at once. Instead of just submitting one run for ANC, just use 20 patterns. So it fast tracks the process for us. So we can basically easily create a variable loading pattern in a short amount of time.
Okay, now on to a brief overview of the loading pattern optimization. So if we look at what was previously used, the old industry standard was the out and in, which is where you place the fresh feeds on the periphery. This is good for minimizing your peaking factors, but bad for vessel fluence, bad for utilization of the fuel. So we moved away from that and went towards the low leakage pattern, also known as L3P. And this was developed to improve the fuel efficiency. So the way that this works is the fresh feeds are placed in a so-called ring of fire, kind of concentric rings in the core of fresh feeds in a checkerboard-like pattern. So this was done to utilize the fuel more and reduce vessel fluence. So Seeing as the point of this project is to extend the cycle to 24 months, utilizing this strategy is better for our case. So if we look at the original core layout, again, 121 fresh fuel assemblies, it uses the L3P. You can see the red is where the fresh feeds are. And there's two rings that you can kind of see where they're placed. There are 52 fresh fuel feeds, 56 once burned, and 13 twice burns. And this uses a maximum enrichment of 4.95%. So this only lasted 18 months, which is current industry standard.
Here are known methods on how to reach our FDH limit, which was our primary safety constraint as we continue to optimize our core, as it represents the localized power in the core. This means that while the core is operating at an average power, the local power can be much greater. If it's too high, then the fuel cannot be properly cooled, which may lead to fuel melt. Our first method involves shuffling the fuel assemblies in the reactor core, where we can move more reactive assemblies outward along with less reactive assemblies inward to help smooth our power distribution. Our second method involves raising the power in certain locations in the core by either raising a feed fuel assemblies enrichment to 6% or by reducing the amount of burnable absorbers present. Our third method to deal with peaking in specific locations is to increase burnable poisons in high power locations or lowering the burnable poisons in lower powered locations. In order to meet our next constraint, which is the end of cycle boron concentration, which helps show us whether our loading pattern met our extended cycle length goal, it was necessary to increase the amount of excess reactivity by increasing the number of fresh fuel or by increasing the feed assembly enrichment. As boron concentration is also dependent on the amount of burnable absorbers, we can also alter this to meet our 10 ppm at end of cycle. Lastly, we can meet our pin burnup limits by ensuring most of our twice burned fuels we utilize are closer to the periphery. Next slide, please. Here we will show you some of the tips that we use to help us optimize the core, and specifically we'll look at the core shuffle, power increase, and the use of burnable absorbers. Next slide, please. Our first method deals with shuffling assemblies around the core. As you can see on the before portion on the left, we have a lot of power closer to the center of the core, as you can see with the higher peaking. To deal with this, we moved twice burned fuel assemblies, which are less reactive than once burned, inward to help smooth power distribution and reduce peaking. After the shuffle, you can see the changes in the after portion on the right, as the peaking in target locations has decreased, specifically in the former once burned locations. One way you can think of this method is placing a loud person in a group of quiet people. So hopefully that person be less loud, if you want to think of it like that. Next slide, please. So in order to make improvements to the power distribution of the core, we must also increase power in weaker locations. This is because all our values in the core are relative to each other. One way you can visualize this is wanting everyone at a game to be cheering, right? You don't want people sitting down on their phones looking bored. So in order to increase power, one of our methods involve increasing the enrichment for the fuel assemblies. As you can see in our highlighted locations, we increase our feed assemblies from 5% to 6%. This will also help us meet our extended cycle length as it provides more excess reactivity in the core. However, by increasing the power in our target locations, the peaking will also increase in these locations as the power distribution shifts. Next slide, please. From our previous slide, we expect our ring of fire to increase in peaking as we increase enrichment. In order to deal with this, we need to introduce more burnable poisons in our higher enriched feed assemblies to suppress any peaking, as we see with our purple circle. However, as our goal is to create a smooth power distribution, as we raise power around the ring of fire, we need to help the weaker locations too. As you see in the light blue or teal circle, we want to increase power in the center as we increase power towards the outside of the core previously to maintain the smooth power distribution. We do this by reducing the amount of burnable poisons in our feed assemblies placed in the center. Furthermore, as we increase power in different locations of the core, we need to continually balance the power distribution. As we raise power in the ring of fire and the center, we must also raise power closer to the periphery. This is seen in our green circles as we lower the amount of burnable poisons present. Next slide, please. After many iterations and a lot of changes to our original core loading pattern, we were able to finalize the core loading pattern for cycle 31 boundary waters. As you can see in our table, we were able to meet all our primary considerations, such as FDH, MTC, and boron concentration at the end of cycle. For our loading pattern, we utilized 56 fresh feed assemblies, with about half being 5% represented by the red boxes, and the other half being 6%, which are represented by the yellow boxes, with different combinations of IFBA and GAD rods. From our previous cycle, we utilized all 52 once burned fuel assemblies, represented by the blue, along with 13 additional twice burned fuel assemblies, represented by the green. As you see in our full core map, our ring of fire primarily consists of our higher enriched fuels, while our inboard checker pattern primarily consists of the 5% feed assemblies. Next slide, please. To help visualize how our core changes throughout its cycle, we generated some plots for our primary safety constraints. Our first image on the left shows how FDH changes from the beginning cycle to the end of cycle, compared to the limits that we were given. We also include when our burnable absorbers, such as IFBA and GAD, burn out to show their impact on FDH. As you can see, our most limiting value occurs at about middle of the cycle. Our second image in the middle shows how our boron concentration changes from beginning to end. As we expect, the boron concentration decreases with burnup, and our most limiting condition is about 16 parts per million at the very end, at 690 effective full power days. Our third image shows how MTC changes from beginning to end. Our most limiting condition is at the beginning of cycle, which is what we would expect as we have the most boron present. As you can see, our MTC remains negative throughout the entire cycle, which is the goal. Next slide, please. Lastly, we wanted to present how our primary safety constraint changes from beginning of cycle to the end of cycle throughout the entire core. Here we have 3 core states: beginning of cycle at about 4 effective full power days, middle of cycle, which is about 345 effective full power days, and end of cycle, which is 690 effective full power days. At the beginning of the cycle, we see that our power is towards the center of the core, as a lot of the higher peaking factors are found here, as the once burns from our previous cycle have a strong effect on the beginning of cycle. As we move towards the middle of cycle at 345 effective full power days, we see that all our once burned assemblies are essentially weakening in their effect on the core power distribution, with the checkered feed fuel assemblies and the ring of fire rise in relative peaking to the rest of the core. As the core comes to its end at 690 effective full power days, we see that the power distribution shifts outward, with most of the peaking being closer to the ring of fire. For the most part, our 6% enriched fuels maintain high peaking factors throughout the entire cycle, and were our primary limiting factors for FDH. Now I'm gonna hand it off to Amadou to show us the rest of our safety concerns.
Thank you, Chris. So in order to make sure the loading pattern is viable, we have to check some safety analysis, and this like the goal of this project is to develop a viable loading pattern. We're also gonna make sure it's good enough for licensing. So I to basically have to check all of the safety parameters and make sure everything is safe according to NRC standards. So first of all, we're going to start with the radial enthalpy rise limits. Chris talked a lot about this in the start, but we know, as Chris told you about just now, we know this F delta H represent the localized power in the core. While the core is operating as average power, there is like some changes in the localized power in different subchannels in the reactor. But we just want to make sure like that there's not peaking on localized power that can effectively cause a fuel melt, as Chris talked about just now. As you can see here, we consider 2 states for all rods out, all the control rods out, and all the control rods inserted into the core at the insertion limit. This shows you for both of those cases, and you can see at the beginning of cycle, you can see the effects of the burnable absorbers that we use in this project. You can see the peaking factors went down, and as these burnable absorbers begins to burn out, you can see the middle of the core, they start to begin to rise up, and then at the end of the core, it all starts to go down. So in this case, you can see, as we've shown here so far, for the all rods out FDH limits, it was around 1.55. All of our F delta H met those limits. So it basically just shows you this loading pattern is viable because it passes this F delta H entropy rise limit. And we know at the rod insertion limit, the axial offsets can be skewed to the highest possible value. And you can, from the graph shown here so far, the highest possible value is even lower than the all rods out limits. For the rod insertion limits, it was given to us to 1.66. This basically includes 8% uncertainty that was placed on us by Westinghouse. This includes 4% for engineering uncertainties and 4% for calculation uncertainties, and which basically just showed our loading pattern meets all of these constraints, and it's viable based on those rudder entropy limits so far. So moving forward, we also have to check the peak pin burn-up. One important criteria for this project here, we know the standard, the industry standard right now is like 5% highly enriched fuel, and using 5% highly enriched fuel, like the maximum value of peak pin burn-up you can get is around 63,000 megawatt days per NTU. But with this high enriched fuel, there's a limit of 70,000 megawatt days per NTU. We try to push our maximum value closer to this limits because we're trying to show here in this case we can use high enriched fuel that can be safe, and also we can increase the max pin burn-up. So just to show you, we can utilize the fuel a lot more. Utilizing the fuel a lot more means we can have less waste and less waste, and basically just it's good. We can get the most out of the reactor, which can indeed in the future help with economic for the future cycles. So yeah, the limit was 70,000 megawatt days per NTU, and it met the standards of like around 69,000 megawatt days per NTU. And one other thing we check here was the rod ejection analysis. In this case, we consider both like the hot zero power and hot full power. The rod ejection analysis is based on like a rod ejection accidents which can occur when there's a mechanical failure in the pressure housing of the rods. We know this is like an extremely low probability event, and the consequences of this rod ejection may include like a large rapid power increase, an increase in the fuel and collapse temperature, and a departure from nuclear boiling. We don't want this. So Westinghouse gave us constraints from the hot zero power conditions and hot full power conditions. All of these constraints you see so far in this table include some uncertainties. Some has like 12%, some have 10%. So for here, we basically just should for this that our loading pattern is viable enough to meet all of this rod ejection analysis. So to make sure if there's a rod ejection at some point in operation of the cycle, it's still safe. We check for the maximum injected rod work and for the beginning of cycle and end of cycle for both the hot zero power case and hot full power. So yeah, so our loading pattern passes the rod F delta H limits, and now it passes the rod ejection limits. And moving forward, we check the shutdown margin, and the reactivity for the shutdown margin is that it's basically reactivity that we need at the end of cycle for the core for us to basically take the core down to subcritical for shutdown. The limits placed on this, including uncertainties also, was around 1700 PCM. It was given to us by Westinghouse, and we made this value it's around 19,000 PCM. We would have wanted this value to be higher, so around 2100, but 1900 is a really good value. It passes the limit that was placed on us, and we showed here a bunch of eigenvalue constant that we got from this that we're using for the calculation of this shutdown margin. And moving forward, we talked about economic analysis.
So whenever we look at the economic analysis, we have a rough estimate of how much just the core would cost. So first looking at it, we see that the total value of the core is around $47 million. And then the second most important number would be the cost per megawatt hour produced, which is around 4.662. So much like the 3-loop team, these numbers are higher than the traditional values that you would find for, say, an 18-month 5% enriched core. However, with the continued use of the higher enriched, it's expected that one, the amount of fresh feed assemblies used would reduce, and two, the cycle link itself is a major contributor to why this would be used. So for example, if you look at the common denominator between an 18-month cycle and the 24-month cycle of 6 years, the 24-month cycle reloads 3 times, so that's 3 months of outage in 3 cores, whereas the 18-month cycle will have to reload 4 times, 4 cores. So you have 1 less core and 1 more month of operation, which is largely economically beneficial to the companies that are running this. So in summary, our F delta H boron and moderator temperature coefficients were all met with sufficient margin. We used 56 fresh feed assemblies, which is less than half and is fairly on par with what is historically used for this core. All of our safety conditions were met, such as the rotted F delta H, our peak pin burnup, our rod ejections and shutdown margin with sufficient margin. And the core is potentially economically viable, maybe not for this iteration, but for further cycles down the line. And are there any questions?
So just a quick note, we just want to say thank you to our Westinghouse advisors, Mr. Durham and Mr. Baxter. It's been great working with you guys, and it's awesome to work with this project, and you guys have been so helpful and guiding us through this path. And also to Dr. Ivanov and Dr. Avramova, thank you for all the help this semester. I'm going to open the floor to questions now. So any questions so far?
I'll ask you one. You may have showed it, but I forgot what it was, but I don't remember what cycle they're on. And my question becomes, are there enough cycles left to get a payback? Or is this plant old and near its end of life?
So this is cycle 31. We aren't given specifics of which core this is. That is proprietary to Westinghouse, so we don't know whether this is nearing the end of the licensing for the reactor, but it is 31 cycles in.
And also, just to add to what you just said, in developing this loading pattern, we in consideration, like in the back of our minds, we think about the core life. So that's why we try to use this pattern close to the L3P pattern, putting the less reactive fuel, the once and twice bond in the periphery, just so that we can increase the core life. We don't know like if this cycle is going to go more than 31st cycle, but just to say we give this core like an extra breathing room. Just try to like increase the core life by putting the less reactive fuel at the periphery of the core, just to increase the core life. Did that answer your question?
Yes.
Thank you.
Thank you.
I got a question for you. This is George Lipscomb. I think you mentioned it, but there may have been something on a slide and you can just point me to it. Maybe I missed it. But you talked about the distribution of power in the core and the distribution, trying to keep it more uniform. Did you look at some calculations regarding that? Or was it just something that you were trying to keep more subjectively equal? Like across the core, the power distribution. I think you talked to trying to keep it uniform, but I don't know if you showed a slide or something with that.
You want to get that, Chris? Oh, sorry.
Oh yeah, I'm thinking of how to answer it. So as we developed the different loading patterns, we took a look at the core map in terms of like the distribution of peaking factors like FDH. We didn't necessarily make any calculations as ANC does that all for us, so it'll give us all the peaking factors in all locations. But we just made small changes, like we said, in the optimization part to make sure that the power, because as everything is relative to each other, making changes in certain locations will affect other locations. So the power distribution was just kind of done kind of like by hand, by just like taking a look at how it is and then employing our methods to make the power distribution relatively smooth, if that makes sense.
Yeah, so more you're saying more manually rather than, you know, producing actual data or maps or anything on it is what you're saying. You kind of just
Yeah.
looked at it manual. Okay, that's fine. I was just wondering if I missed something.
Any more questions?
There is one. The core simulators, ANC in this case, have been used and tested for enrichments up to 5%. Do you think anything would need to be tested or changed in ANC to use it for higher enrichments?
So I can get this. So obviously we need to change the cross sections for higher enrichments. Those changed. It starts in this project. Our advisors from Westinghouse, Mr. Durham and Mr. Blaine, they basically provided a whole library of these enrichments that we're supposed to use for all the fuel type that were given to us for the 6%, 7%, or 5% that we're going to use. So in my thinking, the ANC is good enough to handle like 7%, but the only thing that needed to be changed was the cross-sectional libraries, and those were given to us. So because if we had to generate the cross-sectional libraries as we try to develop a learning pattern, it would take a lot of time. So a big thanks to Mr. Baxter for generating these cross-sectional libraries for us. And so yeah, so we don't need to change anything for ANC. We just assume ANC can handle 6% and 7%. But the only thing that was changed for us was the cross-section libraries. Did that answer your question?
I would also like to add briefly to that. So we actually did run into some small complications with that whenever we were trying to get our solutions to converge at certain burn-up steps. So we solved that by increasing the amount of iterations the ANC would run that particular burn-up step. So there were some small problems at the beginning, but with more computational time allotted, it did converge the solutions.
I'll ask you another question. George Lipscomb again. And maybe you said this. How many cases did you run when you did your comparison, approximately?
A lot. So
100, 10?
No, with a bunch of cases. I know we have a lot. Like it's over 500, and like
okay.
as we talked in the beginning, like we develop a program that basically helps us like develop this in a faster time, so we can basically submit 20 runs to ANC. So it's a 500, but we basically develop something that reduces the time for those.
Sure. Well, my question, I just wanted to kind of get an idea of how many you ran, because did you run into the constraints that you were given? Was there certain constraints that were causing you the most difficulty in meeting the design constraints for your project?
Yeah, absolutely. So the biggest constraint would be F delta H, R odds N F delta H constraint. So since this is a smaller core, 121 assemblies total, there isn't many places to move whenever we're shuffling. There isn't many places to shuffle as say a 3 loop. So whenever we're looking at peaking, which the main way to alleviate that problem would be to take, you know, an assembly that has lower peaking and then swap it with one that has high. Whenever you don't have as many assemblies, that's a problem. So I would say that would be the biggest constraint with our iterations of the core.
Also to add on to that, we used all of the once burned, or all the feed from the previous cycle, which is our once burned. So we were limited by the amount of once burns that we had to help us smooth out that power distribution. So we had to essentially either use twice burns or add in new feed assemblies in our core. So we were limited by that too.
Did that answer your question?
That was good. Thank you.
Thank you.
Okay. Thank you very much, team.
Thank you.
Sure.
Great. We have team 6.
Yes, hello.
Yes.
Hello.
So we are Team 6. Give me a second. We're the accident-tolerant fuel coating methods for fuel rod inner surfaces with team members Robert Carlson, Robert Gentile from South Carolina, who we refer to him as Bobby, Nick Jocelyn, and then me, Liam. With our faculty advisor, Dr. Kay, and industry advisors, Patrick Davis from DNF and Russ Fawcett from GE. As well as we had a lot of assistance from Ryan, which we'll thank later. Robert?
Okay, so why exactly do we need inner diameter coatings and accident tolerant fuels? So accident tolerant fuels are a sort of new thing that have come up a lot recently because of what happened, especially at Fukushima Daiichi, and just finding ways for our reactors to be a lot more safe and to avoid the sort of hydriding and other things that were happening because of the plant conditions of that accident. And so what we're looking to do is use these inner diameter coatings to help prevent against the hydrogen buildup in the in a LOCA accident. And it also will, if there is some sort of rupture or something, it helps mitigate further hydriding from the rupture. Okay, next slide, please.
So on the forefront of creating these accident-tolerant fuels, GE Hitachi has taken the initiative to focus on some outer diameter coatings. And two of the outer diameter coatings that they have used are ironclad and armor. So ironclad, it's a mixture of iron, chromium, and aluminum, and it's resistant to high temperature steam and air up to 1200 degrees Celsius. It shows little corrosion in both boiling water reactors and pressurized water reactor environments, and it is highly abrasion resistant. However, there are two main concerns with it, as it is permeable to hydrogen and tritium, and it is also a parasitic neutron absorber. So to follow this up, GE Hitachi has created this outer coating called armor, which stands for abrasion resistant, more oxidation resistant. So unfortunately, the chemical composition is proprietary, so we cannot disclose that. It is thermally compatible with traditional Zircaloy 2 cladding. It is fret resistant and shows minimal weight gain during steam cycles to prove its corrosion resistance. And this is used to prevent zirconium oxide from forming on the outer surface layer of the Zircaloy 2 cladding. Next slide, please.
Okay, so some of the different sort of coating options for the inner diameters that we've looked at. One of them is the chemical vapor deposition, where there are gases that are injected into a vacuum chamber and then heated until they are able to deposit onto the surface of the workpieces through chemical reactions. Some of the advantages of this is that the precursors will only react with the surface of the workpiece, leaving little waste products in the coating. It is not a line of sight process, so as long as the gas is able to interact with the part, it is able to coat, and it can enable multiple rods being coated at once. Some of the problems are it must occur in a vacuum, and it requires fairly high temperature to catalyze the reaction, which would make it extremely hard to get a full fuel rod of 4 meters to be coated in most CVD sort of machines. Atomic layer deposition is slightly different. It allows for multiple single atomic layers to be deposited onto the surface through CVD. So it's you can get much more creative with the sort of layering you're using, as well as the exact coating options. And that can allow for thicker coatings once reaction sites have been exhausted. Though some of the limitations as well, it still needs to occur in the vacuum, and it's still pretty scarce literature to help exactly figure out how well it works. Next slide, please. So some of the other ones we were looking at ceramic and plasma sprays. Plasma sprays were a fairly good option because it's heating a gas up to a point where it's hot enough to spray onto the thing, whatever is needed. But with most of these, it is a line of sight sort of process. So it needs to be able to, as you move it and pull it out, it needs to be able to see, I guess, everywhere. As well as with the high temperatures that is needed with a plasma spray, you can expect some annealing or some heat problems that can affect the actual cladding. With the ceramic spray, it's a ceramic physically sprayed onto the surface, which is extremely economical and pretty effective at heat and corrosion depending on the certain ceramic that you're looking at. It's fairly easy to apply and geometrically forgiving, but just like the plasma spray, again, it's a line of sight process, as well as the chemical compositions of these ceramic sprays are often extremely proprietary, and it's hard to find non-proprietary research on the similar sort of coatings. Okay, next slide, please. And then the last couple that we were looking at was using sputtering, which is where we have an inert gas that will fill a gap between the metal target and the coating surface inside of a vacuum. And a magnetic field is used to sort of push knock the ions and atoms out onto the other surface. It results in a very thin coating and it's pretty uniform, but it's extremely expensive and not very useful with different geometries. And then last one we looked at was electroplating, which it's simply just using ions between anodes and cathodes, and as they pass through, they will plate a certain source. This will be talked about further on later in the presentation. Next.
So there are several major checkboxes for the material to meet before we can actively pursue it as a coating material. The four major requirements that they have to meet things in are neutronics, chemical properties, mechanical properties, and coating limitations. So several neutronics constraints: it cannot be a parasitic neutron absorber, and it must be permeable to neutrons for the moderation process to take place. And we also have to make sure that the coating material doesn't have any activated isotopes that could potentially create more chain fission reactions. For chemical properties, we want it to be chemically compatible with the fuel pellets and its fission products, and we don't want any chemical reactions through that can harm the system. We also have to ensure that it is chemically compatible with the coolant, and we need to make sure that it does not react with water or hydrogen in any harmful way. And we have to make sure it is also a corrosion-resistant material. Some mechanical properties constraints that it must meet: it has to have good thermal conductivity, it must be abrasion-resistant, it must be resistant to thermal expansion, and it cannot form eutectics at low temperatures. And it has to be able to sustain high temperatures for long periods of time. And as far as the coating limitations, we have to ensure that there's a uniform coating, and we have to ensure that the coating thickness is on the order of microns. So it has to be thin enough to complete all of the above constraints, but thick enough, or not thick enough to complete all of the above constraints. Next slide, please. So two of the initial materials that we looked into were titanium nitride and titanium aluminum nitride. Both ceramics both have very high corrosion and erosion resistance. They don't chemically react much, if at all, so they are very chemically compatible with both the fuel and the cladding. They are both highly abrasion resistant, And the aluminum addition in the titanium aluminum nitride, it introduces an oxidation resistance at high temperatures. And it is generally just improved toughness under extreme conditions. And then below you can see a property table containing some key points for the titanium nitride. As you can see, the melting point is very high, and the thermal conductivity is high as well for a ceramic. Next slide, please. So on the metal side of things, we looked into chromium, pure chromium. So high purity chromium it's got strong corrosion and abrasion resistance. It has a high melting point, and it has good mechanical properties as well. And it does not have a high neutron absorption cross-section in comparison to other coating materials, such as nickel. So we don't have to worry about the parasitic neutron absorption. It is easily obtainable, relatively speaking, and it's got a higher thermal conductivity, higher yield strength, and higher Young's modulus compared to what you see in common zircaloy. Next slide, please.
So as we looked through a lot of these methods and materials, we decided to narrow down to about 2 options. So one of our first choices would be plasma spray coatings with a ceramic. We thought it could be possible to fabricate or engineer a plasma sprayer that could be small enough to enter the less than ½ inch diameter cladding and then slowly pull out. But that also means we had to design something that would be able to evenly coat it, a plasma sprayer that can go through 4 meters. So it was a little bit of a challenge to decide between this or electroplating, which electroplating, as explained earlier, is we would submerge the cladding into some sort of bath or fill it with solution and then try and plate it with a pure metal, because electroplating can only be allowed pure metal. Ultimately, we decided to go with electroplating because we thought it could be more feasible due to things like cost, testing, and various other aspects that we have Nick to continue on.
So, like Liam just mentioned, our down selection process ultimately culminated in the selection of an aqueous electroplating process as our inner diameter coating of choice. And the reasons for this are pretty easy to understand. It's very low cost. That's attractive from an industry perspective, and it's a mature technology. It's been around. There's a myriad of technical and commercial articles and information on how to go about performing this process. And most importantly, it's just feasible. It was feasible for us in the university's provided laboratory setting. You know, plasma spray torch could provide a very strong titanium nitride coating, but unfortunately it's beyond the scope of what we felt we were capable of doing. So electroplating to us seemed to be the process that was the most feasible while still being able to provide a coating on the inner diameter of the zircaloy cladding that would stand up to the demands of environmental conditions in a LOCA accident. So electroplating is great because you can put a variety of different metals, chromium, nickel, copper, and it allows a very thin and a very even coating depending upon your anode geometry and how the bath is arranged. But if that's done properly, then you can get a coating in the 20 to 30 micron range. You know, limitations, unfortunately, you are limited to a pure metal. The process does have to be done aqueously, and there are various pre-treatment processes that need to be performed to ensure that metals can be electroplated and can be electroplated evenly. Next slide.
So because our project was more experimental in nature, we decided to determine the feasibility of electroplating pure chromium onto our zircaloy cladding. We were so graciously provided some old claddings to test on. So we had a full 4 meter long piece that we were able to cut and do multiple tests on various pieces. So our original experiment design is shown on the right. Ideally, it's a chromic acid solution. It fills the inside of the tube with end caps that have been 3D printed, with the central anode fed through the center of the tube. So to provide an even coating and even electric field so that the ions can plate evenly across the entire inside diameter. So for our anode, we decided to use a titanium because we found a patent from multiple years ago that described they used a titanium anode, so we decided that that would probably be the most feasible option. And then we conducted tests to determine the feasibility of it. Here's some of our work in the lab. If you notice, that's on the left picture, that's Bobby, Robert Gentile, and Nick. And then Nick is on the right. Beautiful, beautiful work, guys. So our original experiment. So for our experiment, we wanted a solution because the solution better plates. We found information that says solution better plates when it's heated up. And then we had to set a current of approximately 42 amps and a voltage of about 50 volts. It's an approximate because the solution is getting heated and then cooling, so the resistivity and such will change with time. So that one is an approximate, but we had ways to measure it. So we applied it to the titanium anode for about 15 minutes. After about 15 minutes, we dropped the current and then checked the inside of the tubing. After checking the inside, we realized that most of the chromic acid solution had been either evaporated, leaked, or lost due to electrolysis. We realized the titanium anode had thick signs of residue on it, but didn't show any oxidations. Ultimately, under optical microscopy, we checked the inner tube, and it showed no signs of plating.
So after our first iteration of the experiment, we realized that there was no chromium plating visible on the inner diameter of the zirconium tube. We had to go back and try to troubleshoot as to why we were not seeing any electroplating. So one of the reasons that we came up with was that the diameter of the central anode was too small, and that potentially the anodes was the improper material. So there's a property of an intrinsic property of materials called resistivity. So different materials, titanium, whether it be lead, stainless steel, carbon steel, they all have a different resistivity. And the resistance in an electrical circuit is equal to the resistivity times the length of a particular wire divided by that wire's cross-sectional area. And what when you do these calculations, you find that in comparison to a material such as lead, another type of material that's recommended to be used as a plating anode by the plating literature, you'll see that the resistivity of titanium is roughly double that of lead, leading to a resistance within the wire of more than double that of lead. So if you have too high of a material, too high of a resistivity, you're going to get too much resistance. And if that material's cross-sectional area is too small, and in the case of our titanium anode, it was less than a millimeter. It was less than a millimeter in diameter. You're going to get too much resistance. If you have too much resistance in the wire, you're going to get excessive heating. And at steady state, if you double the resistance, you're going to get double the dissipative power in that wire, and as a result of that, at steady state, you're going to get double the temperature just for over a reference value. So we thought that because of this, what's happening is the wire is getting too hot in the solution. The solution's not being adequately agitated, so you're not getting any convective heat transfer associated with that. And as a result, we're getting nucleate or film boiling on the surface of the wire, and that's preventing ions from being moved to the surface of the grounded workpiece, the zircaloy cladding. So next slide. So after consulting the plating literature, we found that there is a recommended for inner diameter tubing plating operations, there is a recommended inner anode diameter related to the tube inner diameter. And that can be seen by this extrapolated plot on the right. This was just taken directly out of the literature, and if you extrapolate a value based upon our given tube ID, what we find is that the ideal diameter for our anode is about 0.05 inches, or roughly 1.049 millimeters. So, and that's, again, that's taken directly out of the sources we were able to find on recommended anode diameter, and that's entirely because you need to have a central anode that it has enough cross-sectional area that can handle the current you need to pass through this, because these, especially chromium plating solutions, are hexavalent, and they require lots of current to ensure that those +6 chromium ions actually make it to the grounded tube. So it's a very inefficient process, and thus you need a lot of current. So this is why you have to be able to have a sufficient anode diameter to be able to handle that current safely. Next slide. So after taking this into consideration, we decided to make a modification to our initial, experimental setup. So what you'll notice is different about this is, rather than having two end caps, one on the top and one on the bottom, we removed one of the end caps and left the bottom portion of the tube open and placed it in a dish of chromic acids plating solution. So what we found, and the reason for doing this was to ensure, A, we wouldn't have evaporation of the solution as we had in our initial setup. B, we could agitate the solution with a stir bar, so solution could freely move in and out. We wouldn't get any sort of local depletion. And then also, because we have the solution in a dish, we can set that dish on top of a hot plate, and that hot plate enables us to hold the solution at a constant temperature. The plating literature recommends for chromic acid solutions that you need to have about 150 degrees Fahrenheit temperature. That's ideal. And if the temperature drops too much, your current also drops, and the efficiency of your plating process goes down. So this was our updated experimental setup after taking into account the need for a larger central anode and the fact that we were getting loss of plating solution in our original experimental design. So next slide. Here you can see the bottom portion of the zirconium cladding that was submerged in the chromic acid solution. The material that we went with was stainless steel. Now, stainless steel can be used as a plating anode, though it's recommended that a lead tin alloy or platinized titanium be used, but those, to get pure lead wire of a certain diameter is difficult to find, and we were operating under some time constraints, and oftentimes to get either a lead tin alloy of a specific composition or a pure lead wire of a certain diameter, you have to special order that, and there are lead times. But Ryan suggested we go see Irvin in his office downstairs of Burlington, and he was able to supply us with a stainless steel anode, and that's what you see here. So unfortunately, it wasn't the ideal diameter that we wanted to use. The ideal diameter was about 1 millimeter, a little over 1 millimeter diameter, and this anode, this wire that was on hand was about 3 millimeters. It's all right to oversize your anodes, your plating anodes, but you just don't want to undersize them. So if you undersize them, then you could end up with excessive heat and a situation where your anode's not capable of handling the current you need to pass through it to get the plating process to proceed forward. So next slide. So what was the result of this? Did the increased anode diameter work? Was it able to actually deposit a chromium plating on the inner diameter of the zirconium tube? And the answer is no, it was not. Based on what we were able to see, we do not see any. We were not able to see any chromium on the inner diameter of this on the tubing using the optical microscope. There is some black spotting that's seen on the right side of the photograph, but we're not sure what that is. We didn't have the instrumentation necessary to determine what that is. Dr. Calme's graduate student Ryan hypothesized that it was pitting, but what that is ultimately anyone's best guess. So, yeah, unfortunately, based on what we're seeing, this looks very similar, with the exception of the black spotting, to the unplated sections of zirconium tubing. So, next slide. So after our second experimental iteration, we regrouped and we brainstormed as to what remaining cause could be causing the chromium to be failing to deposit onto the surface of the central of the zirconium cladding. And we don't believe it's an insufficient anode diameter. We didn't believe it was nucleate boiling on the anode. We didn't believe it was a lack of plating time. In typical industrial plating applications with chromium, the work pieces only stay in the bath for 1 to 2 minutes, and we were plating over 30 minutes and not seeing any chromium on the surface. So we don't believe it was a failure to hold the anode in the center of the tube. We were very careful to make sure that the anode was directly in the center, and we don't believe that there was a lack of consistent power or anything like that. So the three causes that we were able to think were most likely culprits for why it's not working were an improper material. So we used stainless steel rather than lead, and that we also used titanium, but we could use lead or lead tin alloy or platinized titanium, but we didn't have access to those materials, so we didn't use them. We think it's possible that there could have been some grease or some industrial lubricant or something on the surface that we weren't able to remove with our initial perchloric acid etch. But again, we don't think that was all that likely, although it is possible. But the biggest culprit that we all agreed on for why we were not seeing a chromium plating on the inside was an improper surface treatment. So the patents that we were able to find in the experimental literature recommended to use ammonium bifluoride, and due to safety concerns, we stuck with perchloric acid. So I'll leave it up to Liam to go from here.
Yes, as Nick described, we realized that our surface treatment was lacking. The perchloric probably wasn't effective enough in treating the inside of the tubing. We found literature that talked about more ammonium fluoride, HF, so ammonium bifluoride, to treat the inside or to etch the inside of the rod so it's properly, so that the chromium can properly adhere onto the inside of the tube. So it recommended between a 1.2 and 3 ratio for adequate metal coatings. Next.
The following excerpt at the right is from a research article published in 1979 from Sandia National Labs. And essentially what it says is that they found that the most effective etching solution, a pre-treatment solution for plating zircaloy 2 with nickel, was ammonium bifluoride. They later go on to recommend that a heat treating process would improve adhesion performance an hour after plating, and they also recommend potentially threading, literally cutting threads into the surface of the zirconium to improve mechanical adhesion. But again, this is another research article from the 80s that we were able to find during our troubleshooting process as to why this why the ammonium bifluoride pretreatment is so essential to ensuring that the electroplating process can deposit metal onto the surface of zirconium and zirconium alloys.
So with our experiment, it got cut short because our experiment was working up through March. That's when the COVID-19 situation happened. So we weren't able to continue having more trials. But it did help expose us to a lot of the information in materials science, like electrochemistry and electroplating, optical microscopy, the need for ATFs, and then how to properly handle materials and do analysis for it in the lab setting. We want to give a special thanks to Dr. K for supervising us and guiding us through this process, as well as allowing us to use his lab. Special thanks also to Ryan, who helped us a lot and helped supervise us in the lab. And ideally, we would like to continue more experimentation, but with the situation as it is, we have been unable to continue to do so. I'm going to open the floor to any questions.
I got one.
Yes.
George Lipscomb here. More just kind of a step back question. When you were starting your presentation talking about the coatings for accident tolerance and the various different materials you were looking at and whether they, the proper techniques for putting them on, and then you started talking about, actually going into doing the electroplating and the difficulty with that. And I've seen electroplating, and it's a little bit of an art when you do it. And so I'm kind of surprised that you went down the path of actually trying to become somewhat experts in doing the electroplating with materials that are maybe not typically used. So can you explain a little bit about the project? Were you looking for more of a theoretical coding and maybe like a literature-based or a technical-based research as to, is this something that could be done in zircaloy in the middle, on the inside of a fuel tube, or was the whole purpose of it to actually go ahead and do it and see the results of it?
Well, I can answer that. So it's a little bit of both. So first of all, we weren't trying to figure out exactly how to scale this up to 250,000 tubes a year, which is the quota the quota that we were given typically for industrial zircaloy tube manufacture. That's about how many they would need. But we primarily wanted to demonstrate a proof of concept that we could actually get the coating on the inside of the tube. Ultimately, after speaking with GE, they were interested in a feasible process to do so because, ATF research is typically concerned with outer diameter coatings, and there's a good reason why you don't hear about inner diameter coatings because it's very difficult to get a coating evenly all the way around the inside of a tube because most of the processes are line of sight. There's very few processes effective. I mean, even to a certain extent, electroplating is still line of sight. You can't put your plating anode on the outside of the tube. It's going to preferentially plate to the outside. So, with the exception of CVD is the only process that wasn't really line of sight that we looked into, and that wasn't feasible for us to try. So it was both, is it a feasible to do, and what process could we find that could actually get this coating on the inner diameter of a fuel rod rather than just around the outside.
There's another question, and I'm gonna, this will be the last one so that we can get going on the last group. The question is, zircaloy will form a thin oxide layer pretty quickly, even at room temperature. Would that account for some of the surface effects?
Based on the research that we did, that's absolutely why it would, at least that's what we presume would cause the lack of plating and lack of adhesion. But yes, zircaloy and zirconium alloys, zirconium in general, forms a very thin oxide layer in air, even at room temperature. And these ammonium bifluoride, which is basically a mixture of ammonium fluoride and hydrofluoric acid dissolves part of the zirconium too. So when you do that pretreatment process, you're dipping it in that etchant and it's actually dissolving the zirconium, a small amount of the zirconium, and presumably that oxide layer that forms on the surface. So it's the whole point of doing this etching process is you're getting that oxide layer that's not really even visible under the microscope, and you're removing that so you have fresh, unoxidized zirconium alloy for which you can plate to. So yeah, we think that's absolutely, it's the oxidation on the inside that's causing those surface effects, that's preventing the chromium from ultimately being deposited onto the inner diameter of the tube.
Thank you, team.
All
Can
right,
I?
thank you very much. Thank you.
Team 7.
Good afternoon, everyone. My name is Jennifer Jeffcoat, along with Ben Austin, Cade Brinkley, and Jacob Weinberg. Along with us is our advisor, Dr. Benjamin Beeler, and we're partnered with Savannah Riverside with Dr. Tracy Stover and Tara Smith. Our project is the Mark 18A Target Material Recovery. Next slide, please. Just a little background information. Appointed by the DOE, the California Production Campaign began August 11th, 1969 at the Savannah River site. They was responsible for producing and managing heavy isotopes. 86 targets was highly enriched plutonium-242 Mark 18A outer housing targets was irradiated for the purpose of producing californium-252. The interest in californium-252 is that it is used as a possible portable neutron source that can be used in applications such as fuel rod scanning, reactor startup, and activation analysis. The campaign shortly ended a year later, around November 8th, 1970, changing the objective to producing plutonium-244. For about a decade, the Mark 18 targets continued exposure until they was decommissioning. 21 of those targets was transferred to the Oak Ridge National Laboratory to extract the californium-252. The remaining 65 targets were stored at the Savannah River site in water basin storage. In 2012, Savannah River site and Oak Ridge National Laboratory was appointed to address the disposal of the remaining targets in a study identifying several options. Some of their options included looking into the possibility of recovering the Mark 18A target materials, partial recovery, or dispose the Mark 18 targets as waste. The study highly recommend that the targets be processed to recover the plutonium-244 and heavy curium. Next slide, please. Which leads us to our problem statement. Savannah Riverside supplies heavy curium and plutonium-244 in the remaining 65 targets from the California Production Campaign. The amount of the isotopes within these targets is unknown, tasking us to perform a computational analysis to find isotope inventory, utilizing the information for economic target reprocessing decisions. Next slide, please. With that in mind, we decided with 2 design methods, utilizing a scale code. The first method was grouping or binning targets based on similar irradiation histories. And our second method was to individually model each target with unique irradiation histories. More detail will be given in the next slide.
So a little bit about SCALE. SCALE was developed by Oak Ridge National Labs Reactor and Nuclear Systems Division. It combines Monte Carlo and deterministic solvers with integrated data libraries, and therefore is used for a wide variety of modeling, such as reactor physics, shielding, criticality, safety analysis, and activation and depletion analysis. The relevant modules to what we wanted to do were mainly the Titan reactor physics module and its T depletion sequence, and the Origin activation and depletion module, along with Origin's libraries, which contained all the necessary cross-section and decay data. Next slide. So for each of these SCALE inputs, a few things were needed. They fit into two categories: target assembly geometry and neutron flux. The assembly geometry has the physical dimensions of the target along with its material, the isotopic concentrations, densities, all of that. And these irradiation histories, as Jen mentioned, were over 10 years. So the reactor was often refueled, which would change the isotopic concentrations in the driver fuel. So that would also need to be known as part of the geometry. And the second category, the neutron flux. The neutron flux is a very hard number to know a lot of the time. So we used assembly power as a surrogate, and this will change based on the target location in the core. And we'll talk more on this later. Next slide. So the exact assembly geometry dimensions and many other things were classified, as this is a government reactor meant to produce californium. So the exact assembly dimensions are classified, as well as the exact driver fuel enrichment, the core dimensions, pitch, etc., fuel to moderator ratio, or really anything else that would allow for an exact replication of this reactor. However, what we did know were the assembly and target heights. The assemblies were 6 feet tall, with the plutonium targets only sitting over the middle 4 feet of that. We know a uranium-235 content within the driver fuel, 120 grams in each assembly. We know that there's 180 grams of plutonium in each target. We were told that heavy water was the coolant and moderator, and we had a general idea of what the assemblies actually looked like. They're 4 annuli, 3 inner annuli of uranium aluminum alloy, and an outer plutonium target. Next slide. So to get our input files, we had to make several assumptions. The main ones being those dimensions. We based the dimensions on widely available aluminum pipe for ease of manufacturing. We were suggested to simulate the uranium as 90% enriched, and aluminum was neglected in our neutronics analysis because it has a very low cross section relative to everything else. And we also assumed that any axial variations in composition would be negligible, since the targets, which are what we're interested in, only fit over the middle 4 feet of the assemblies. This all leads to one main limitation: just having inaccurate isotopic amounts at the end of irradiation relative to the real actual target composition. But if a high resolution study was conducted, we would still be able to get relative amounts to make informed decisions on processing these targets. So that's actually what drove our decision to choose to irradiate or model each target individually. Next slide. So this is our model. The 3 dark blue circles in the center are the uranium aluminum driver annuli, modeled after 2, 2.5, and 3-inch inner diameter Schedule 10 aluminum pipe. And the light blue ring is the plutonium target assembly, which was modeled as 3.5-inch inner diameter schedule 40 pipe. And the green background is the heavy water moderator. And next slide.
So this is the face map of the K-reactor core. As you can see, it's got a hexagonal lattice, and it's kind of hard to see this just because of the resolution of the picture, but we actually have X coordinates and Y coordinates on this face map, which is how it was communicated to us where the targets would be located in the core during each specific radiation history. So we used the placement in the core to calculate the power in each assembly. We had to assume a distribution. We picked the sinusoidal distribution because it was easier to work with. We didn't know exactly where the uranium assemblies were placed in the core, and the targets themselves moved around significantly according to the radiation history. Next slide. So this is a couple of just rough sketches of how we modeled the flux profile. The top image shows the entire profile from end to end, which also extends out beyond the core. We created a relative extrapolation distance, assuming a peaking factor of 1.35. I say relative because you could just go back one slide, Jake.
Ben, we're having problems hearing you. Can somebody else on the team pick it up?
Can you hear me?
Yep, now we hear you.
You can hear me now?
Yeah.
Okay, Jake, go back one slide. So I say a relative extrapolation distance because if you look at the number of elements in X direction and the number of elements in the Y direction, just because of the geometry considerations of the core, the actual unit distance between each one of those nodes were different. So if you go to the next slide, you can see that the profile is actually a little stretched along the Y direction, and that is because of the extra number of entities in that direction. When creating the profile, we took that into account and normalized them to make sure that they were still weighted the exact same relative to the actual physical geometry of the core. Next slide. So this is a kind of a video of the placement of each one of the targets during the irradiation history. As you can see, they move all around the core. Again, we don't know where any of the actual fuel assemblies are, but the targets do move around a lot, which you can see now why it was important to actually model these individually as opposed to groups. There are really no three distinguishable groups that you can really see. Next slide. This is mine too. So some of the strategies we use in our scale code, I think some of these were already mentioned before by Cade. Initially, we neglected the aluminum content because of their low cross-section. We later on had to add them to the target portion of our model because of the very, very low fuel densities that we were having. We had to increase the density so that our simulations would stop diverging. Because we used, I think there were 4 different fuel drivers with different uranium contents in each one of them, instead of creating several other geometries for these specific fuel drivers, we essentially created a timeline to change the density of the uranium-235 inside those assemblies. We also tested out the number of cross-section libraries, the number of times that they calculated the 252 group cross-sections based on the amount of radiation time in each one of those cycles. To make our lives a lot easier, we created a MATLAB code to help create the input files so that if we did happen to notice a change in one assembly that had to be made, we can efficiently make the changes to all the other assemblies and all at once. And we only track specific isotopes, specifically the plutonium-244 and all the curium isotopes, as well as the californium-252, just to view how it grew over that first year during the californium production campaign. Next slide.
Okay, awesome. So now it's time to talk about the actual results that we got from our simulations. So we have two tables here. The top table gives us a quick summary of the assemblies that had the most and the least remaining mass of plutonium-244. So we can see that assembly number 46 has the most, assembly 36 has the least. And if we look at the bottom table there, that's all the curium isotopes. Savannah River was mostly focused on heavy curium, so those are the asterisk curium isotopes there, 246, 247, and 248. And you can see that assembly 39 had the most, assembly 46 had the least. So when we saw these preliminary results, we noticed a trend, at least with assembly 46, it had the most plutonium, but the least amount of heavy curium, and we're gonna investigate that further. Okay, so these three graphs just give you all an idea of how the plutonium-244 and heavy curium isotopes are produced and how their masses change throughout the lifetime of the simulation. So the first 10 years was when the reactor was operating. The final roughly 41 years, the reactor was shut down, which is why you're seeing pretty much no change in any of the mass concentrations. And then that first year during the Californium campaign, the power is significantly higher than in the subsequent years, which is why for plutonium-244, you see such a massive jump as well with the heavy curium isotopes. So to really understand the mass distributions and the power distributions throughout the assembly in the reactor, we made heat maps of those distributions. So the things that you can look at visually is that in the assemblies, and so each box here is an assembly, they're in no particular order, but the darker the color, relatively the higher mass or amount is in that assembly. So in plutonium-244, the assemblies where we have a lot of plutonium-244, we have a low amount of heavy curium. We also noticed that in those assemblies with a lot of plutonium-244, we had a lot of curium-245. And the best way we could relate that to the simulation was the average assembly power. So what was mentioned earlier was how we use assembly power or power in the reactor as a surrogate for neutron flux. Well, we were able to attribute an average power to each assembly. And looking at that, we can really see more of what's in part influencing these distributions here. So in assemblies where we have a high average power, we have a low amount of plutonium, but a high amount of heavy curium. So, and we also threw in californium-252. That is the maximum californium-252 produced. And you can see higher the power, the higher californium produced. So to quickly summarize why we're seeing these trends, if we consider the actual production chain of californium-252, once we reach plutonium-243, it can naturally decay to americium, or it can absorb a neutron and become plutonium-244. And once it becomes plutonium-244, it's a lot more difficult in order to create californium. But as you can see here at the bottom, it can become plutonium-245, which will eventually become a source for californium, or sorry, not californium, curium-245, which is why we see a lot of curium-245 when we had a lot of plutonium-244, because our production term for that isotope is increasing. And lastly, these are just some other heat maps of the other curium isotopes we were tracking. They weren't a particular focus in this study, so I'm just going to show them so you can see them. We'd be happy to talk about them, but again, they weren't really the focus of our simulation. And this time I'd like to open the door for any questions.
Thank you.
Any questions?
That just means we did a good job presenting if there are no questions. So I'm okay with that.
I would have to agree with you on that one. Well, nothing in the chat. If you're asking the question to yourself, remember to unmute.
Yes, Weinberg did speak. He was the last one who spoke. He had the mustache, yes. I think we all kind of have mustaches, though.
I've been working on it for a pretty long time. This is a big deal for me.
Mm-hmm.
If no one has any questions, I'd just like to go back and talk more about
Oh yeah, he can go on all day. Let him,
production.
I'll mute.
So this was something that was really interesting for me when I was going through the results of the simulation, and I still don't have the perfect answer for this, but I was pretty shocked to see that the assemblies that had a relatively high amount, it was almost exactly flipped with heavy curium. So about 50 of the 65 assemblies matched perfectly in terms of plutonium mass concentration and heavy curium. So that means the assembly that had the most plutonium-244 had the least heavy curium, the second most plutonium had the second least heavy curium. That makes sense. And I would have thought that we would have seen, especially with how complicated the neutronics of this is and how there's so much more that's going on than just this one chain here, where we would get something that seems almost inversely related. And that's how we kind of came across the production of plutonium-244, which produces to 245, which then decays to curium, which actually curium is in this production, or yeah, curium-245 is in this production chain, which can then of course absorb another neutron and continue on to produce heavy curium. So and another thing was that as we increased power, or what we would assume increasing the neutron flux in the assemblies, we actually did not have an increase in plutonium-244. In fact, if we lowered the assembly power, we would actually produce more plutonium-244 relatively, which we had also thought that was a bit weird, because we expected if we increase our neutron flux, we're going to have more of those neutron capture interactions. But again, it kind of talks to the complexity behind this production chain and all the other neutronics and interactions that are going on, that even if we do increase one thing, it's not going to directly relate to another. So there's a lot more going on. It's not just a simple dichotomy.
If I could just add something there, Jake.
Yeah.
One of our hypotheses there was that the half-life of the plutonium-243 was a lot less than that of 244. And so it could be that the source of the plutonium-244 is just dissipating too quickly, while the plutonium-244 is still interacting with had a cross-section of 90 barons, if I'm not mistaken. And so that was one of the things that we were thinking about, but yeah, sorry to interrupt.
No, you're fine. Kind of closed out my thoughts. So if that piqued any other questions or insight, we'd be happy to hear or answer any.
Okay, looks like no further questions.
Well done.
Okay, all right. So first, I would like to thank all of the groups for their work, especially that this is on a two-phase, work style, starting in the fall with 1 credit hour under 406. And of course, a lot has been achieved, although it was only 1 credit hour. And then the completion comes into 408 in the spring with full 3 credit hours. And everything was going well until we got this, COVID-19. to interrupt us. It didn't interrupt us dramatically. I have to admit this because we were able to still function and to continue doing, all whatever we can do. The only thing that was maybe dramatically affected, it was group 6 with Dr. Kawami because they were in need for lab work. But as we shut all the labs, so they have to stop and they have to work with what they already collected. However, I really applaud to you all and I say that this was an exceptional exercise during this semester, during this time, and I congratulate you all. And of course, congratulations on your achievement. And soon you will be graduating with your degree. Thank you so much.
Dr. Boham, Dr. Boham, Dr.
Yes.
Boham.
Yes.
I want to take this opportunity to thank you and Ms. Marshall for actually working with our students, SC State students, and we hope that this partnership will continue. We thank all the colleagues that work with them for their support, and also thank you to our students for doing the job. Well done.
Thank you, Musa. Thank you. Of course, there was, a scheduled meeting, but unfortunately, we haven't had the chance to meet as we used to. Hopefully, things will open up, and then either we come to you or you come to us.
That would be nice.
Yes.
Lovely.
Lisa, thank you so much.
You're very welcome. Thank you.
Yes, ma'am.
So, Lisa, are you taking a picture of them or what?
I will.
I'm going to do it.
I believe that those that did the judging should send the completed forms to Dr. Borum, and I'll put his email address. Well, everybody knows Dr. Borum's email address. It's borum@ncsu.edu. If you all could send that to him, and thank you once again for joining us for 7 teams that have worked very hard this last academic year, and hopefully that showed in the presentations. I think it did. I'd like the team members to remain on for me to do what is now known as the Zoom picture. So for everyone else, thank you and have a good evening. And then for the team members to stay here, please.
All right.
Nice job.
Very
Thank you, everyone.
Thank you, Lisa.
Thanks, everybody.
Thank you. Nice job.
Everybody.
Good job.
It really does make it easy to pick the
Thanks,
audience.
everyone. You did a great job.